And welcome back, Astronomy 1010, to our second homework session. This will be our third lecture and third lab today. We're going to be doing chapter S1, that special chapter S1, following chapter 3. Let's see. I've got the homework for you guys here. If you go to your homework tab, we should see something. Let's see. Come on, Blackboard. Oh, I love Blackboard. I love it every day. I sing its praises. Here we go. Okay, can you guys see this? The questions are right here. We're going to be doing this is homework number 2, chapter S1, problems number 28, 41. Sorry. That has got to be a typo. 28, 1, 2, 3. That simply cannot be right.
38.
Yeah, wow. So I made a typo there. I should edit that right now. Is it, what's 38? Is that opposite rotation, Brandon?
Yes, it is.
That's the right one. The 28 sounded too low. I like the numbers a little bit higher than that. Okay. Wow. Thanks, Brandon. Let me submit that. Good thing we're doing this together, huh? Here are the questions. Does everyone have that? Everyone feeling like they've got it together? Hello. Nice to see everyone this morning. Hey, man. Hi, Ryan. So what do you think? Should we get right to it? Amber's got her fuzzy pencil out. That means business. Brandon, since you seem to have it together more than I do, would you be kind enough to read us? The first problem is one I did not quite get to. I was just about to cover this topic. So we're going to kind of fly blind here, but let's just do it. Brandon, read it out for me. It's called, oh, sorry. Wait, Brandon, can you give me the numbers again? 38.
Oh, yeah.
All right, I can look them up too. 38, 41, 47, 51, and 53 ABC.
I thought my mic was unmuted. It wasn't. That's why I was talking. You couldn't hear me.
That's okay, dude. We're all in it together, kid. All right. So our first problem today is, don't forget to put your name on the page too, right? You guys might want to set it up similar. Ooh. Don't forget to put AS1010 somewhere up here. Our first problem is chapter S1, problem number 38. And it's called opposite rotation. All right. Brandon, take it away.
All right. Opposite rotation. Suppose Earth rotated in a direction opposite to its orbital direction. Suppose it rotated clockwise, as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day?
Sidereal day.
Oh, sidereal day. Explain.
Okay. So this is a question you're not going to have any clue to the answer of because I didn't cover solar day versus sidereal day. So let's try to do this. Students, how long does it take Earth to spin once on its axis?
24 hours, right?
What if I told you that that was a lie? What if I told you that they've been lying to you this whole time? In fact, the true spin of Earth takes 23 hours and 56 minutes. How can this be? We've been told our entire lives that the spin of Earth, a day, is 24 hours, and yet it's actually 23 hours and 56 minutes. That's because you do not track time by the spin of the Earth. You track time I track time badly by the sun. Okay, let's take a look at how this works. I'm going to go to share screen for a second. Oh, and this is a good reminder that I need to call up my various slideshows. I want this one, and I want this one. Okay, so let's take a look at the solar day versus the sidereal day. Normally, when you see Earth from above, Earth spins counterclockwise and orbits counterclockwise. And I had a picture of this in my first slideshow. Now that I think about it, I showed you a picture like this, showing the Earth spinning counterclockwise on its axis and Earth orbiting counterclockwise around the sun. In fact, we even defined counterclockwise as which direction in space, students? Which direction did we define the counterclockwise spin of Earth as? Oh, shucks. I thought we remembered things. I thought we knew stuff. Counterclockwise means what in space? We have to start there.
What do you mean by that? What do you mean by that question? Like, not simply like what is the counterclockwise movement, right?
I understand your confusion, Dennis, but while the question seems, we define.
Like
Pardon?
It's not just like like as simple as I think I'm thinking it is, right? Like the
Well,
rotation. What is?
It's simple if you understand it, and it's complicated if you don't.
Yeah.
In space, we define north, south, east, and west in a particular.
Yeah.
And counterclockwise refers to one of those directions.
It's east.
Counterclockwise is east in space. This is a critical point. It's a critical point. It's not something, Dennis, that you would think of on your own. But I attest that in our previous lectures, I told you that we define counterclockwise as east in space. If
Gotcha.
you look, provided you look at counterclockwise from above, and this is a subtlety here, but if the Earth is spinning like so, if you're looking at it from above, I'll make you the camera above. You can clearly see that this is counterclockwise, right? That's opposite the direction a hand on a clock would go.
Yeah.
That's as seen from the North Pole. But if that spin were to be seen from the South Pole, it now becomes, wait, is that clockwise in the camera? Yeah, it's now clockwise relative to you. Do you see what I mean?
Yep,
So
I gotcha.
The Earth's spin is just in one direction. We define it as east as seen from above. So I was just trying to get you to remember that, Dennis. Nothing else to it. Okay.
Right, thank you.
Yes. But that can be a confusing point your first time around, because that's not a thing that you would think of on your own, right? Just like black holes aren't something you'd think about on your own. You need an astronomer to tell you about them. Okay. So with that in mind, let's take a peek at what's going on as Earth does its rotation. The Earth is not stationary in its orbit, but if I can use the annotation key here, as Earth is spinning counterclockwise, oops, in this direction. Sorry, my mouse is a little low on batteries. Actually, there's only one way to do this right, and I want you guys to follow along with me and make a diagram. We're gonna have to do a little extra on this problem because we didn't do it in class. So leave yourself a little bit of headroom, and I want you to draw the sun. And this is going to be the normal view. This is not the problems case, but this is how things work normally. I also want you to put an Earth over here. And I want us to draw an arrow that represents a local observer's meridian. And I'll talk to you about the meridian in just a moment. So I want you to draw an arrow that points directly towards the sun. This arrow represents a local observer's meridian. Dennis or anyone else, can you remind, I've got a frog in my throat this morning. Can you remind me what the meridian stands for? What does the meridian mean? From our class notes.
It's a arch that rises due north and reaches the zenith and
Zenith?
sets due south.
Exactly. That's Megan, right?
Yeah.
Yeah, that was Megan.
Megan, I'm just going to rename you because it's showing me your email, Megs808, and I can get stupid sometimes. So I don't want to forget to call you Megan. Okay. Yes, Megan, technically you are correct. It's a line that runs north to south through your zenith. But what does it mean psychologically or spiritually or something like that? Let's look at a picture of the nighttime sky and see how it rotates. I do believe I showed you guys this picture. I think it's slide 79 of star. Wait, I'm not sharing my screen with you, am I? Let's try that again. Did you guys get to see this picture before? I think so, right? Talk to me.
Yes.
All right. This picture shows you stars rising and setting in your local sky. Megan, can you show me where the zenith is? You might even be able to take control of the mouse, or can someone show me where the zenith is on this picture?
Zenith is at the top of that. Oh, sorry.
I'm sorry, not the zenith, the meridian. I'm sorry, I didn't wake up that long ago. I'm still getting it together here. The meridian. Where's the meridian in this picture?
Is it above the horizon? Above the top of that green kind of oval shape, up to the top of the up to the zenith?
Well, that sounds like the entire sky to me. Everything north of that, everything above the green disk is your local sky. The meridian isn't the entire local sky. It's a line that cuts through it. So try better, Dennis. You might know what you're talking about, but you haven't said it correctly yet.
All right.
Wait, Dennis, can you take control of my mouse? Can I allow you to have control here?
Let me see.
The students in my 1010 class could do that.
So the entire local sky would be what I just pointed out. So.
Wait, where are you? I don't. No.
So this would be the entire local sky right there, right?
Yes, that's the entire local sky. If you mean that in a three-dimensional sense. Okay, you can draw on my thing. Cool. So I can draw on. I can draw on it too.
Yeah, I think I figured it out. So the meridian.
Can you just show me with your marker what the meridian is? Here, let's clear all drawings so that we can make it neat. Oh.
Sorry, I'm kind of struggling. This would be the horizon, right? Sorry.
The horizon.
That right.
That's the horizon. Yes.
That's the horizon. That's the local sky. Why can't I think of the meridian? I'm sorry. Sorry about that.
That's okay. We're still figuring out the technologies, but we see you have to know what the meridian means for us to go forward here, or things are going to get confusing.
All right,
and that's okay, Dennis, but let's figure it out. Now, Megan, what was your definition again? Repeat your definition.
The arch that rises due north reaches the zenith and sets due south.
So can someone draw that in? Like, it's nice of you to say that and all, Megan, but if you can't point where it is, then we're effed, you know?
Would it be that right there?
No, that is not sufficient, Dennis. Because can anyone draw it in?
It's I can't draw it in because for some reason it's not letting me, but it's from
wait, Dennis, how did you do it? Let's find out how Dennis did it, because this could be a tool going forward for the entire class. How did you draw on my thing?
Oh, I figured it out.
Okay.
Let's
clear all drawings first. Okay, try now.
This is the prime meridian right there.
Don't say prime meridian.
Oh.
Say meridian.
Meridian.
The only reason, Brandon, is the definitions matter a whole bunch here, and that's what's going to start tripping us up as a class. The prime meridian is a longitude line on Earth. The meridian is a line on your sky. And Brandon has done it absolutely correctly. Let me add to his drawing with some shocking blue. Okay, watch. You start north, you go up through the zenith, and then you set south. Can you see that? That's the meridian. Now, what is the psychological function of the meridian? If you can watch the motions of stars as they rise in the east, come up to your meridian, and then set in the west, the meridian is the halfway point in the sky. Class, suppose the sun was on your meridian. What time would it be during the day if the sun was on your meridian? Oh, snap.
Would it be noon because it's the halfway?
Yes, Tess, that is my point. Excellent. If the sun is here, if it's on your meridian, that's supposed to be your local 12 o'clock noon because it's, as Tess says, the halfway point of the sun to the sky. That's kind of how ancient peoples devised solar time. They kind of want, and by the way, when you do time by a sundial, that's what's called in astronomy apparent solar time. So you guys know what this, let me clear all drawings here. You guys know what this guy is, right? F520, this is a sundial. And in a sundial, they have a stick. This is one of my favorite words in the English language. This is called a gnomon. And the stick casts a shadow so that when the sun is on the meridian at the highest point in the sky, it'll cast a shadow right at 12 o'clock noon. Okay, I'm being a little long-winded here, but I want to make sure we understand. So here, I want you guys to come back to my drawing. If this arrow represents an observer's local meridian, what time is it now if you are standing where the arrow is?
Noon?
Very good. Let's label that. 12 p.m. Okay, normally, students, the Earth is orbiting around the sun in a counterclockwise fashion. And as it's orbiting the sun in a counterclockwise fashion, it's also spinning counterclockwise. So let's draw in 1, 2, 3, 4, 5 Earths. Okay? And let's imagine the arrow is spinning counterclockwise, and we'll draw it, you know, every kind of 90 degrees in its rotation. As it spins like so, the next meridian arrow will point down as the Earth rotates. Then your meridian will point to the right. Then your meridian will point up. Then it will point back to the left. And now I'm going to draw one more meridian that points towards the sun. Which one of these represents a true 360-degree spin of Earth? Oh, let's label them. 1, 2, 3, 4, 5. Which of these Earths represents the true 360-degree spin of Earth?
Would it be 4?
Yes. But I ask you, Brendan, is it 12 p.m. and 4? Yes or no?
No.
Why not?
Because it would be 12 hours, so it would be 12 a.m.
No. Listen. All right. Whoa, I thought we were talking, and then I realized that you were missing the point there. All right, let's try this again. I agree with you that Earth number 4 is a 360-degree spin. That's a spin of Earth, you told me at the beginning of our lecture, or office hours, was supposed to be 24 hours, right? Now you're telling me it's 12 hours. What the shit is it? I can't figure it out. How long does it take Earth to spin on its axis?
20, well, not 24 hours.
Not 24 hours.
What was it? It was 23 hours and 56 minutes?
Very good.
Okay, I see.
Is it noon at position number 4?
No,
Why not?
it would, because of the actual,
Yeah, I'm kind of giving this to you all backwards, but focus on the arrow. If it's noon o'clock, which direction should the arrow point?
at the sun, right?
Right. So this here must be 12 noon, right?
Yeah.
This, number 5, is 24 hours.
Ah,
That means, students, that there are now 2 types of day, a solar day and a sidereal day. This question, position number 4, is known as the sidereal day, and this is known as the solar day. I need to erase that and take some definitions for you guys. But let's give you a second to catch up for me.
I can't really see the writing.
I'm writing too small, Dennis.
Well, I don't know if you're writing too small or if it's just a little blur. Yeah, all right, that's perfect right there.
Sorry about that, dude.
Oh, no worries.
I'm writing a little small. Keep in mind, I'm used to kind of teaching this stuff in class where I have a big whiteboard and we're all in the same room. So sometimes it's hard to modify my style. But that's better, right?
Yeah, it's just it's not on the screen right now.
What?
It's on some. It's on. It was just on someone in the class. So.
Look, we got to talk about how you use Zoom. Could you please go to speaker view? Or Dennis, in the upper right-hand corner, there's a little button that you can switch between speaker view and gallery view.
Oh no! It just for some reason it just went to someone else in class. I wasn't touching.
That's because they were talking. So listen, Dennis, find my little picture at the top or the side and double-click on my little picture, and that goes to lock speaker view. For instance, if I double-click on your picture, I can lock you as the speaker, and now you're looming large on my screen. You've got to lock me into speaker view so that when other people talk, it doesn't take me away. Does that make sense? So double click on the little picture of me when you're in speaker view.
All right, hold on. I'm doing it.
That will freeze me as large when other people start talking. Does that make sense?
Yeah.
All right, so I call that locked speaker view, and you have to lock me in so that when other people cough or talk, it doesn't take my screen away. Okay, so Dennis is copying that down.
All right, I'm good.
All right, you're good. All right,
Thank you.
let's do something here before we answer this question. This is my bad. I didn't quite get to this last time, and this is making this problem more complicated than necessary. There are 2 types of day. And let's just write this down because I think this will help us answer the question. There is the sidereal day. I don't suppose anyone out there knows what the word sidereal means. It's related to Latin. Sidereal means with respect to the stars. Okay? Think of it as a star day. Sidereal day is a true 360-degree spin of Earth, and a sidereal day takes 23 hours and 56 minutes. A solar day is slightly different. It is the time for the sun to orbit the sky. In other words, the time for the sun to go from noon to noon. The time for the sun to cross your meridian again. And that solar day is a 24-hour clock. The reason why there's a difference is because, as you can see in my share screen here, it is because Earth is in motion around the sun that by the time it completes a 360-degree spin, so it's spinning and it's rotating as it orbits around the sun, it completes a 360-degree spin, but it's moved a little bit in its orbit, so the sun is no longer in the direction of the arrow. You've got to rotate an extra 1 degree to point back to the sun. That extra 1 degree of rotation corresponds to about 4 minutes. And that's why there's a difference. Keep in mind, if Earth did not orbit the sun, if Earth was just spinning on its axis like so, and it stayed in the same position, there would be, so this line could represent an observer's meridian. if the Earth just spun on its axis, but it didn't orbit the sun, there would be no difference between the solar day and the sidereal day. It would take a 360-degree orbit, and the ancient Babylonians would have defined that spin as 24 hours. But the people who invented time were tracking the sun, not the stars. By the way, you can also think of the sidereal day. You can add one more definition in here. The time for, sorry. The sidereal day is also the time for a star to orbit the sky. Okay, that got a little wordy there. Could you read question 38 again for us, Brandon?
Yes. Suppose Earth rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise, as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day? Explain.
All right, let's write down our givens. The Earth's spin is clockwise, but the Earth's orbit is counterclockwise. The counterclockwise orbit is the same as it normally is, but this is new. Before I help you answer the question, does anyone want to take a guess? Would the solar day and the sidereal day be different if the spin was in the opposite direction?
Would it be minus 23 hours and 56 minutes?
Well, what do you mean by minus 23 hours?
I was just taking a guess. I didn't have any reasoning behind it.
All right. Let's try to draw the picture and let's see what happens. Let's draw the same picture we did before. Leave yourself some headroom. And down here, I want you to draw on the left side of the paper, draw the sun. On the right side of the paper, draw Earth. Draw an observer's meridian pointed towards the sun. Label it 12 p.m. because we know that's noon. Now we're going to draw the Earth still orbiting counterclockwise, but we're going to show the spin in the opposite direction. Let's label it 1, 2, 3. Oh, shoot. I want to draw 5 Earths, and I've got to do this correctly here. 1, 2, 3, 4, 5 Earths. I'm not doing a great job at art this morning. Okay, which way should I draw the arrows? Can you guys help me there? In position 1, which way is the arrow going to point? The meridian arrow.
Words.
I'm sorry, who said that?
Down.
Oh, Amber, can you tell me which way?
Down.
Let's see. Down would be opposite the direction. Isn't this counterclockwise, Amber?
Yes.
But we're spinning clockwise now. Do you want to revise your answer?
Oh, so would it be upwards?
That's correct. Okay, Amber, keep going with me because you and I are talking. Which direction would the arrow point in position number 2?
Left.
Left? Like this way?
Yeah.
Which way next?
Down.
Hold on, it's looking like we're going clockwise, counterclockwise again. If you go from here to there, isn't that counterclockwise, Amber?
Yes.
But in the problem, Earth is supposed to be spinning clockwise now.
Oh, okay.
Do you see what I'm saying? So can you help me revise your answer a bit?
So would 2 be going right?
2 will be going right. What about 3?
Now is that one still going clockwise?
We're spinning clockwise the whole time. We're orbiting counterclockwise, but we're spinning clockwise. This can get confusing. So
Yes.
which direction? 3?
Going upwards?
Pardon?
Would it be going up?
But Amber, if you start at 2 going to the right and you go to up, isn't that
Oh.
once again counterclockwise?
Okay, so it would be down. Okay.
Down. Do you see why? Because we gotta keep spinning in this direction. That's clockwise, right?
Yeah.
That's okay. We have to work through this. What about position 4?
Up.
Up? Wait, we can't go from down to up. We have to go 369, 369 like a clock, you know?
So it's going, what's my left? Left?
Left, right. But do you agree with me that in between going down and in between going left, we're going to have to point back towards the sun first, right? One of these is a solar day. One of these is a sidereal day. Amber or anyone else, can you tell me which is which?
All right.
Amber, you did great.
The sidereal day would be 5,
Very good.
and then the solar day would be 4.
Can everyone see why he said that? Brandon, I'm worried that, I hope everyone followed why you said that, but I'm worried that maybe. Brandon, can you explain that in case someone didn't follow us?
Because the solar day always points towards the Earth.
Right, this is 12 noon again, right?
Yeah.
Well, actually, it's not exactly 12 anymore, is it? Okay,
No.
Brandon, read the question one last time and then tell me the answer since you seem to understand it. Let's find your little face too while you read. Where are you? Where's Brand? Where are you? Oh, there you are. You're at the end. Okay. Read the question and answer it.
Suppose Earth rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise as seen above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day? Explain.
What have we learned?
That wouldn't both of the days be flipped technically? So the
When people say flipped or opposite, I don't always know what that means. So I want you to be more specific than that.
would the sidereal day now be 24 hours and the solar day be 20?
No, because the rate at which the Earth spins has not changed. The rate of the spin has not changed, only the direction has changed. So what does that mean? I'm intentionally not giving you guys too much guidance. I want you to think through this. How long does it take Earth to spin on its axis?
24 hours.
False.
23 hours and 56 minutes.
Does that change because the direction changes?
No.
Okay, so how long does a sidereal day take?
23 hours and 56 minutes.
That never changes because the rate at which the Earth spins doesn't change. How long does a solar day take now, hotshot?
Would that be just 23 hours?
No, it's not a 56-minute difference. Anyone? Anyone help Brendan here? Or is he our best hope?
But
Maybe
it's still
24 hours.
Megan, it would not be 24 hours because the solar day is clearly happening before the sidereal day. Someone else was trying to chime in. Who else was talking to me?
I was going to say 24 hours as well.
Oh, sorry. Do you understand why it's not now, Dennis?
No, I thought it was going to be the same, to be honest.
Okay, look. Do you see that these are happening in a sequence? 1, 2, 3, 4, 5?
Yes.
Does 4 happen before or after 5?
Before.
Good. Now, why does 5 take 23 hours and 56 minutes? That might be the missing link. The
It's
reason
because of the full rotation.
someone else, please talk to me. Who?
It's because it's a full rotation. It goes all the way around. So that's
Yeah.
why it takes 23 hours.
Yes, Tess, exactly. Tess understands. Tess understands that this is the sidereal day because this is a true 360-degree spin. Do you see that, Dennis? If I'm pointing to the left and I'm pointing to the left again, that's a 360 spin, correct?
Yes.
And the spin of Earth always takes 23 hours and 56 minutes because the spin is the same. So my point, Dennis, is that the solar day can't be 24 hours because it came before. In this case, the solar day is before the sidereal day.
And in
How
the
long-
other case, the solar day came after the sidereal day,
Right,
correct?
in the other case, we were spinning the direction that Amber desperately wanted to spin in. Amber has a counterclockwise preference. We can see that. Okay, so which is the correct way. And so in that case, you complete a 360-degree spin first. Let me look at the diagram so I don't mess up mine. In the case of the normal rotation of Earth, you complete the spin first, and then you've got to rotate an extra bit to get back to noon again. Normally, the solar day is 24 hours, and the sidereal day is 23:56 minutes. But in our case, how long is the solar day going to take? Put on your best thinking cap.
Would it be 2350?
50, that's a 6-minute difference.
Yeah.
Stay consistent. You're on the right track, Brandon, but your math sucks, okay? Normally, how much longer than a sidereal day is a solar day?
4 minutes.
Okay, so do the math.
He's a savage.
That's right.
Would it be 23:52?
Booyah! Ding-a-ling,
Oh my
we got
God.
a winner. 23 hours and 52 minutes. Nice, Megan.
Cool.
Okay, you guys, I'm liking your participation. You're making me feel good about your ability to learn. So listen,
We have
what's the answer to the question?
Oh no. I'm gonna play Mario Golf. Is that okay?
No, it's not okay if you play Mario Golf.
I'm so sorry. I didn't know my-
All right. I thought that was one of the students. Sorry. What's the answer to the, does anyone remember what the question asked? Oh my God, it's 10:50.
You want me to read it again?
Yes, I do.
Suppose Earth rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise, as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day? Explain.
So what's the answer to that question?
No.
Okay.
Like,
Would it
No.
be no because the sidereal day takes like a true 360 spin?
Yeah, so now I believe that you guys understand that the solar day will not be longer than the sidereal day. It'll be different. The describing of why, Megan, which you just tried to do, is difficult. What does the arrow represent, Megan?
It's pointing to the sun.
No, what is it? What does the arrow represent?
Oh, the direction.
The direction of what?
meridian.
Meridian. It's the meridian, Megan. So
Okay.
Megan, why does a solar day not longer than a sidereal day? Why is it now shorter? Because
I have no words. I'm not sure.
that's okay. This is a wicked hard problem your first time around. How about I just write them down and you guys copy? Does that sound good?
Yes.
Okay. I've tortured you enough on this problem. Here's how we answer it. If the Earth were to spin clockwise while orbiting counterclockwise as normal, then no, the solar day will not be longer than the sidereal day. That's our first sentence. In fact, the solar day will now be 4 minutes shorter at 23 hours and 52 minutes. That was all you, Megan. You did that. Now for the why, and this is the hardest point. To explain why, you have to focus on that little arrow that's rotating, and then you've got to think about what that arrow is. That arrow represents a local observer's meridian, because that's how we're keeping track of the motion of the stars and the sun. This is because a local observer's meridian, let's underline that because that's kind of the key phrase. That is because a local observer's meridian will point back to the sun before completing a 360-degree spin. How's that? Now, I took a long time on that problem, and part of the reason why is I hadn't really covered this concept in class. I'm sorry, we had a lot to cover last class. It was impossible to get it all in, and impossible to do it right anyways. So today I had to teach you the difference before I could teach you the new answer, you know? All right. The next problem does relate to things we learned about in our last class, but the next problem is still quite complicated. I'm just giving a moment for everyone to catch up because I know it takes you guys a while to write after I write. Oh, that says will. Sorry, that should say while. I don't know what the hell is wrong with me. Right? Amber, Dennis look ready to go. Megan seems ready. Brandon, are you still writing?
I'm done. I'm good.
Zach? He gave me a thumbs up. That's cool. Let's see who else is out there. I want to know if I can move on here. Michaela, give me a thumbs up. Ryan, you cool? Janita, you cool? All right, I like it. All right, let's move on then. Here I go. Okay, let's try number 41. Brandon, you were doing a great job, so why don't you read this out again?
41.
Yep. What's the title?
Fundamentals of your local sky.
Okay, read it out.
Answer each of the following for your latitude.
Hey, wait, pause there. What the heck's our latitude? Who knows?
Oh. That is 42 degrees north.
Excellent. All right, keep going.
Where is the north or south celestial pole in your sky? Is question
Is this
A.
part A?
Yeah, this is part A, sorry.
They want to know how we find the location or describe the location of the North Celestial Pole in your local sky. Oh, thank you for that coffee, Jordan. That's wonderful. I've had coffee delivered to me. I'm in heaven. Okay. Also, my forehead is sweaty. Guys, the picture that we want to have here, can I make a recommendation? Last class, I showed you a very important slide. Come on, you buggers. This is the local sky in Rhode Island. This is the picture that you're going to need during this thing. So, shoot, what number was that? I'm dumb. Let's say it was 35. It's a little bit after that. Either take a snapshot of this or call up from your lecture notes this picture. I want you, hold on, let me move to the side. Take a snapshot again, Megan. I want you to have north in the picture there. This picture is the critical picture. Can someone take their mouse and use a color pen and point to the North Celestial Pole in this picture? Let's start there. Let's see if someone can do that. Meanwhile, I sip coffee and relax. I want to get that for the video, so let's get me sipping some coffee. This is a relaxed coffee sip while I wait for the students to answer. Delicious. Nice. Can I make one? Who did that?
That was me.
Brandon, can I make one suggestion to you? Remember
Yeah.
that the sky is the dome. So I would have liked it if you circled that point there. This is the direction of the North Celestial Pole, but remember the entire sky is pasted onto this dome, correct? So can
Yes.
we just improve it and say that that's the North Celestial Pole right there? Yeah, okay. Nicely done. Okay, who's going to describe that for me? How do I describe that point? Do you think we should say it's a little bit to the left of the pine tree above the antenna on my pappy's house? Or should we try to use maybe one of our coordinate systems and talk like a real adult? That was
Talk like a
loaded
real
question,
adult?
obviously. Okay, so which coordinate system are we going to use then? Does anyone know the answer? Does anyone know anything?
Wouldn't it be would it be Polaris?
Polaris happens to be there, more or less. Yes. So if you'd like, we can also, there's Polaris. Okay, let's type Polaris because obviously I can't handle that. Okay, now we got that taken care of. Oh, oops, sorry. Well,
Are we
guys,
looking
oh,
for the latitude?
Amber, could you say that again?
Are we looking for the latitude?
Latitude describes a position on Earth. I'm looking for a position on the sky. So while we need to know our latitude to answer this question, I'm not looking for a latitude per se. I'm looking for something else.
Oh, I got it.
The politeness routine here. Okay, Brandon, you seem ambitious. So what do you got? Then we'll try Dennis.
Would it be 42 degrees?
What coordinate are you giving me?
What the hell?
You're not wrong, Brandon, but you're not fully correct yet. Listen, can I go forward a couple of slides here? Do you guys remember the horizon system? I am looking for an altitude and an azimuth. So when you say 42 degrees, I'm not sure which coordinate you're giving me there, homie.
That's the latitude, I believe.
Latitude is a coordinate on Earth. I'm looking for a coordinate on the sky.
The
North.
of Polaris is equal to your latitude. That would
The
be
what of Polaris again, Amber?
altitude.
Altitude. The altitude. So in other words, okay, Amber's onto something. Amber, I'm looking for an altitude and I'm looking for an azimuth. Can you give me one of those, Amber, specifically?
The altitude would be 42.
42 inches? 42 degrees. Nice. That's correct. What about the azimuth?
It would be 0 degrees or north.
Bam! You're good. Was that Megan?
Yeah.
That's right. That's kind of like what color is an orange, right? If azimuth gives you direction, then the direction of the North Star is going to be north. The direction of the North Celestial Pole is going to be north. Very good. Okay, that was a bit of a struggle, but we got there eventually. Remember, students, you are going to use the horizon system. Altitude and azimuth. Let's move on to question B. Brandon?
Question B, describe the meridian in your sky, specifying at least 3 distinct points along it, such as points at which it meets your horizons and its highest point.
The meridian, as we've discussed already today, Megan, we'll probably need your help because you read it for us last time. The meridian has an arc across your sky, and that means it requires 3 points: a rise, a highest reach point, and a set point. And each of these positions is going to have its own altitude and its own azimuth. So we're actually going to need like 6 numbers here. Maybe you ought to refresh our memories, Megan, with your definition of the meridian.
It's the arc that rises due north, reaches the zenith, and sets due south.
So on my share screen then, oops, let me dial it back a few. Let me shrink you guys a little bit. Sorry. In other words, from Megan's perspective, this should be the rise point. This will be the highest reach point here, and that will be the set point there. Does that sort of follow from your description, Megan?
Yes.
All right. So Megan, why don't you try to give me one of these points and then I'll torture someone else. Let's start with this one, the one I'm pointing to there. Altitude.
Would the altitude be 42 degrees?
No. 42 degrees is up here. But you're down here.
Oh,
Right?
0 degrees?
Very good. 0 degrees altitude, right?
Yes.
So what's the azimuth of that point?
I forgot. Oh, wait, degrees along. Oh, 42 degrees?
False.
What? Oh,
Yeah,
God.
because watch. 42 degrees azimuth, Megan, let me point that out to you. What's an incorrect color? An incorrect color is green, lime green. 42 degrees azimuth would be like over here somewhere. But you are here. Azimuth is your degrees along the horizon. So if you're going to do 42 degrees, you'd be like sliding along over to here, right?
Mm-hmm.
But that green dot is not where you are. You're at the red dot right now. What's the azimuth of the red dot?
Would it be 0 too?
That's right, because it's degrees clockwise from north, and you are currently sitting right on top of north.
Okay.
Nice. Let's write 0 degrees or north. That way you remember that north is 0 degrees. Okay, that was enough for her. Someone else want to try the zenith now? Oh, shit. I screwed it up. I can't forget. All right, the next point is your zenith. What's the altitude and azimuth of your zenith?
Would it be 90 degrees for altitude?
Yep. What about the azimuth?
Where's my diagram? Would that be 90 degrees also?
Nope.
No.
What is the azimuth of your zenith? If I'm located here, what is the azimuth of that point? Huh. What's the closest point to the zenith on the horizon?
$180?
No. 180 is over here. That's south. Okay, I'm just messing with you guys. It's undefined. If you're here, all the points on the horizon are equidistant from you. It's a degenerate point. Remember degenerate points? That was a tricky one. The azimuth is undefined, but we can put a dash because it's undefined. But we'll put at the zenith. What's the set point?
Would that be 180 degrees for altitude?
Nope.
No, it'd be 0 degrees. Sorry,
That's okay. And what's the azimuth then, Brendan?
that'd be 0 again.
False. It's not north.
It's not north. It would be 180 then, right? Since it's
Yes.
south. Yeah.
There you go. Or south. By the way, this could also be called due north. And this could also be called due south.
Cool.
All right. That was tough, guys, but we're getting there. Can I erase? Oh, Ian's just joining the party. Hey, Ian.
Yeah.
I got a bone to pick with you. I dropped 2 people from this class who neither showed up nor submitted any homework. I almost dropped a 3rd. His name was Ian Green. He didn't turn in any homeworks and any labs, but then somehow in the fogginess of my whiskey-soaked brain, I remembered that there was a nice young man named Ian who had attended my lectures. And because actually I had to go back and watch the video to be sure. But because I remembered your face, I did not drop you from the class. So during this public shaming, I want to ask you directly, do you plan on turning in any of the work that you showed up for?
I thought I had.
Oh, then maybe this is a thing we should talk about with everyone. Sometimes, guys, you'll submit stuff to Blackboard and you'll think you're done. But if something glitches out, you can sometimes not submit. So if you tried, that could have happened. Allow me to break the office hours for a second, because this is kind of an important point here. Ian, here we are.
Mhm.
I'm going to go to my grade center. I have 2 assignments from, oh, Megan, you must, oh, that's right. Megan, you had the problem with the HEIC files, right? I have to talk to
I
you.
resubmitted it.
Did you fix it? Hey,
Yeah.
Ryan, you had issues with your submissions too. Did you notice that, Ryan? Are you hiding in the background there? You trolling us?
I did not notice that, but
Ryan, I need you to resubmit because you guys gave me these weird HEIC files. Ian, here you are, buddy.
Mhm.
Oh, Yanita, you've got a problem too. Do you see this? Attempt in progress. Yanita, your homework 1 had an issue. You got to finish submitting it. I know this is kind of new for some of us. Where's
Send me a
Ian?
little receipt.
Yeah, I'm
You know,
still here.
like when you submit, they send you a little receipt or something to your email.
Yep.
That means that you completed it.
Well, right now, you might have gotten a receipt for your homeworks because I can see that, I'm sorry, your labs. You definitely submitted lab 1 and lab 2, and I gave you 10 out of 10 for that. But look at your homework. It says attempt in progress. I don't have a grade for you. That means you were
But I
uploading it.
sent it.
Could you just go back and do it again? Because all I know is what I have on my end. And this is why we're talking. Sometimes you guys will think you submitted it. Ian, I'm not seeing anything for you here. So something got weird on your end, Ian. Do you think you can fix that after class or during tea break, or if you want to ignore me during class, whatever? Where are you? Oh, there you are.
I'm still here. Yeah, I'll work on that after class.
That's
Sorry
cool.
about that.
But I'm not really trying to bust your beans, so to speak. I'm just letting you know about it. You know what I mean? Because you may not have realized. And the same with Ryan. Ryan, you got to resubmit, and Megan already figured it out, right, Megan?
Yes.
You had to go into your settings and choose most
Yeah.
compatible.
And
Right.
I sent it in from like my Safari on my phone instead of uploading it as a file on my computer.
I see. So then you did it a different way. Ryan, if you're using an iPhone, you've got to go into your camera settings and choose most compatible under camera settings. Okay, that's enough of that jazz. Let's get, oh, yeah?
Professor, I don't have the picture anymore. I deleted it, so I don't know how the hell I'm gonna get another one.
You deleted the picture?
Yeah, I don't like keep a lot of pictures on my phone because
Wait, I
like
just
my
want you to
phone is
see me
full.
smash my head into the computer, okay? All
Go
right.
ahead.
Look, I'm afraid you need to, because I can't do your homework for you. That's a little bit on the unethical side. You're gonna have to rewatch the video and rewrite it up. Well,
Yeah,
no, you
but
still
that
have
wasn't
you still have the work in your notepad, right? Or did you throw away the notebook too?
I did not. I changed notebooks.
Then you
So
will
I don't
take
know
it.
where I put it.
Well, I don't know where you put it. So that sounds like a you problem, if with all due respect. You're gonna have to find wherever you wrote that stuff up and take another picture of it, or you're gonna have to rewrite it by watching my videos on YouTube. Thankfully, I've recorded all this, so you can rewatch it and
So
redo
let
it.
me just write it down. I missed homework 1, right? You
Just
didn't
homework 1. That's all I'm missing from you.
Fine.
Okay. Yanita, I'm with you, okay? In spirit. I hope you work it out. And let me know if I can help. But either find what you wrote down the first time or copy it and write it down the second time. It won't take you that long. Okay, let's get back to the show here. I'm going, where were we? Brandon, we're waiting for question C.
All right, question C. Describe the celestial equator in your sky, specifying at least 3 distinct points along it.
Okay, the celestial equator, like the zenith, is also an arc. It has a rise, it has a reach, and it has a set. I'll try to do this one a little neater this time.
We answered this.
Oh, hold on, Brendan. I'm with you. All right, what were you saying, buddy?
We answered this already in last class, so we.
Oh, I just love it when a student remembers things that I say. That happens so rarely. I'm glad that you remembered that I already gave you this answer. So why don't you hit us with it? Hold on, first, Brandon, because answers can sometimes come too fast for your own good. Can I just share a screen real quick here?
Yeah.
Does everyone see where the celestial equator is on this diagram? Hey, let's talk to someone like Zach. Zach, can you draw on my picture?
Oh, let me check.
See if you can draw. This is a cool way for us to
It'd
interact.
probably be annotate, right?
Yep, and then.
Yeah, I can.
Okay, so can you show me where the celestial equator is? Oh, nice. Where's the celestial equator here?
I'm not sure what's that. Right here.
Right, but okay, yes. Okay, yes, I like it. So now I want you to change your color to magenta or orange. And can you show me the 3 points that we ought to describe, the rise, the reach, and the set? Remember, an arc through your sky should have 3 points, a rise, a reach, and a set. Where do you think those should be on the picture here? Have I stumped you or?
Not sure, yeah.
All right, this is important. Does anyone know how to help him? Where's the rise, the reach, and the set? See, it doesn't matter for us. I'm worried that Brandon's about to regurgitate the correct answers, and none of you are going to learn jack shit by that. Oh, who's drawing? Who's the yellow man? Who's doing that?
That's me.
Yes, Dennis. Dennis, make your thing a little smaller. Show me the points like this. Okay? Show me those. Okay, that's one of them. Clear it out. Make the points smaller.
All right, so that one right there.
Like
where the
here.
dot ends, yeah, right where that red line ends.
Hold on, wait, let me change I'm gonna change mine to blue. You make yours yellow. Try one more. Do you mean like this right here?
Right where that, yeah, right there.
All right, show me the rise. That's
then
the rise.
Right
Where's the
at
reach? Dennis, you're with me. I like it, Dennis. Where's the reach? The highest point, the reach.
Right, right up there, like right where that red line like hits.
Can you
that.
Draw?
That.
Draw.
Yeah, let's see if my pencil here work right. I'm trying.
No, draw with annotate. You were doing it before. Yes. Yes.
Right there.
Right.
And then.
Right there. Right. That's your reach.
Yep. And then the last point would be right here. Or nope. Right. No, not right there. A little to the right where that west intersects with that that line. Right there.
That's right. That's the rise. That's the reach. And that's the set. Nice. Okay, Brandon, let it rip.
All right, so the rise would be 0 degrees altitude.
Yep.
And then the azimuth would be 90 degrees. Yeah.
Or east, right?
Yeah, or east.
And that's due east.
Yeah.
Keep
And
going.
then the reach altitude would be 48 degrees. And then 180 degrees. Let's still be east.
No.
No, south.
South.
Yeah. And then the set would be 0 degrees. And then 270 degrees due west.
And that whole thing is due west.
Yep.
Do we understand?
Do you mind just like making it a little clearer? Just real quick. The graph or the chart.
Hold on. The graph or the words?
The words, yeah.
Okay. Dennis, they look clean and clear on my screen. Do they look fuzzy on yours?
I just can't see to the right of where it says 90 degrees, 180 degrees, 270 degrees. I just can't see those words.
Okay, let me try to improve them.
So all right, so it's east, south, and west?
Yeah. I was just adding a little bit. I wanted to say that this is due east, and this is due west.
And then right above that, to the right of altitude is
azimuth or AZ. My abbreviation for azimuth is AZI.
All right, that's what I thought.
Other students, does it look clear or crunchy on your screen?
It looks clear.
Okay.
I'm just using a phone, so it's a little smaller for me.
That makes sense. That makes sense. And you are going into lock speaker mode, right? You're not in the tile mode. Correct? Dennis?
Yeah, I'm good.
All right. Can I erase? Oh, we're doing really bad on time here. I'm going to erase. Really bad on time. Okay, question D.
Does the sun ever appear at your zenith? If so, when? If not, why not?
Okay. To answer this question, we should talk a little bit more about the rotation of the sun around our sky, which is what we're going to do today. Let me go to my slides, and let's look at a cartoon of how the sun moves through our local sky. I'm going to show you two cartoons. This is the slightly more sophisticated illustration, but I don't like it as much because they've pushed north kind of up into the plane of the board. This shows you the path of the sun at 3 different days throughout the year. On the spring and fall equinox, the sun travels the same path as the celestial equator, rising due east, coming up to a maximum altitude of 48 degrees in the south, and setting due west. In the summer, it rises north of east, and it sets north of west. In the winter, it rises south of east and south of west. This picture is a teensy bit more crude, but actually superior because it has north oriented to the right, the same as our diagrams and drawings in class. These 3 arcs show you the path of the sun at 3 different days, 3 different times of the year. The good one to start on is the spring equinox. On the spring equinox, the sun is located at the same point as the sun is located on the path of the celestial equator. So it rises due east, reaches a maximum altitude of 48 degrees in the south, and sets due west. As the days go by, the sun's journey through the sky takes a higher and higher path. Each day it winds itself up a little higher along this trail, rising here, until it gets to the summer solstice. That's when it will rise sort of 23.5 degrees north of east. It'll come up to a maximum height of 23 degrees above the celestial equator, and then set sort of like 23 degrees above west. Although, oh geez, it is this angle here. That's an angle, and that's 23.5 degrees. What's the answer to the question? No? Michaela, nothing? Michaela, do you remember the question?
Yes, it was like if the sun would reach the zenith.
Where's the zenith in this diagram?
Up top, above the arc.
Does it look like the sun is reaching the zenith?
No.
Okay, very good. Hey, what's the altitude of this point?
The altitude was like 48 degrees.
Very good. How many degrees is it from the celestial equator to the summer solstice?
I think you said 23?
0.5.
23.5.
So what do you think is the maximum altitude the sun will reach in the Rhode Island local sky?
So it'll be 42 plus the...
No, 8.
48.
Plus.
So it'll be 71.5.
Damn, you're actually pretty good at this.
Well,
I thought you had... No, but my point is you actually did know what was going on. Okay, this is great. All right, so let's write that down together. No, the sun will not reach the zenith in the Rhode Island local sky, but instead reach a maximum altitude of, let's remember how she did it, 48 degrees plus 23.5 degrees equals 71.5 degrees in the south at noon on the summer solstice. What's the maximum latitude you can go on Earth and still have the sun reach your zenith at the summer solstice? That's an advanced question. This is a question that might bust your brains. How far north can you go on Earth and still have the sun reach your zenith? Obviously, if you're on the equator, the sun's going to reach your zenith on like the spring equinox. Let me show you a couple of different pictures here that'll help. This is what it looks like if you're on the equator. The celestial equator is actually perpendicular to your meridian, and the sun will reach your zenith on the spring equinox at noon. Take a guess. How far north can I go on Earth and still have the sun reach my zenith?
Would that be the North Pole?
Hell no. On the North Pole, the sun will not even get above 23 degrees above your horizon. Shit. I want control of the slide. All right. Do you know that there's only one day on the North Pole, 1 day per year? On the day, let's use yellow for the sun. On the day of the summer solstice, the celestial equator is the same as your horizon if you're on the North Pole. So on the day of the summer solstice, the sun will just wrap itself around the horizon and you'll have 24 hours of dusk. That sounds pretty awesome. And then over the course of half a year, the sun will wind itself higher and higher and higher in your sky until it gets to a max altitude of 23.5 degrees, and then it winds itself back down. Then at the fall equinox, you have 24 hours of dusk, and then whoop, the sun goes below the horizon, and you have 6 months of darkness. The day and the year are the same from the North Pole. And hell no, the sun will never be anywhere near the zenith of the North Pole. That's why it's cold up there. How far north can you go and still have the sun reach your zenith? Answer, 23.5 degrees north latitude, otherwise known as the Tropic of Cancer.
Does that mean that would also work for the Tropic of
Capricorn.
So that it's the exact same then, right?
Well, it's not the exact same because the sun reaches your zenith on the winter solstice in the Tropic of Capricorn.
Okay.
I'm always wary. Sometimes people like to say it's the same or it's the opposite, but they can be internally confused. So it's always better to try to state it explicitly. You'll discover that as we go forward, and we have to be careful with our language here. All right, we're going to go for the big kahuna. I'm cutting off problem F because we're running out of time. But I'm sorry, I'm cutting off problem E, but I want to do problem F. It's very important. Brandon, what does question F say?
What is the range of declination for stars that you can never see in your sky?
This is a challenging problem, and I'm going to walk you through it. We're looking for a range of declinations in which stars are circumpolar. Okay, a range means 2 numbers, and that means the declinations will be greater than or equal to some minimum value, less than or equal to some maximum value. What are circumpolar stars, guys? I've got the coffee jitters. No more of this coffee for me. That's okay. Class, does anyone remember about circumpolar stars?
Write them down.
Did I show you these cool pictures last time? Did you see this picture, 81?
Yeah.
So tell me about circumpolar stars.
Wouldn't
Is
that,
every Oh, yep.
Wouldn't those be the? No, never mind. Oh, no. Never mind. I thought I had it.
Are all the stars in this picture circumpolar? Yes or no? Amber says no.
No.
Amber, which ones are circumpolar? Which ones are not circumpolar?
The circumpolar stars, they don't set below the horizon, so it's where the horizon is.
Yeah. Could you circle an example of a circumpolar star and then circle an example of a star that's not circumpolar? Can you draw on my picture?
I can't. My computer won't let me.
Oh, okay. But your answer was great. The circumpolar stars never set, right? So this star is circumpolar, but this star here is not circumpolar. And as Amber correctly said, the last circumpolar star is the one that just grazes your northern horizon. That's your last circumpolar star. We're looking at a range of declinations. How do we define declination again? What's the definition of declination?
Declination is equal to degrees measured plus or minus from celestial equator.
Good. Let me go to slide 79. Just to make sure that you guys understand declination, this is a local sky view. Brandon, can you tell me the declination of the red ring?
Oh, crap.
It's one thing to regurgitate a definition. It's another thing to understand. I want you to start by regurgitating the definition, so you're doing good. But now I want you to understand. I'm a needy God.
No.
Can anyone tell me the declination of the red ring? Oh, Zach, are you taking class outside in the sunshine? That's badass. What a brilliant idea. Why didn't I ever think about that?
Yeah, it's nice out.
Yeah, I know. I'm looking at it through the window and I'm crying big tears. Okay. You should barbecue while you're at it. Anyone else? Can you tell me the declination of the red ring?
Would it be 0?
Very good, Michaela. You are right there and swinging for the fences. Let's type that in. This is 0 degrees. Michaela, since you're so damn good, do you think you could tell me the declination of the north celestial pole up here? It's
going to get 90 degrees.
very good, but in declination we say positive 90, okay? Good. Michaela, I still want to keep talking to you because you understand me. Do you think you could now give me the declination of this ring here, the teal ring?
Wouldn't it be like the 23.5
It
degrees?
could, but let's say it's about a third of the way up from 0 to 90. What's a third from 0 to 90?
Like 30 degrees?
Positive 30 would be a reasonable guess. Although your positive 23 wasn't an incorrect guess. I see why you said that. But let's go with positive 30. What about the purple ring?
Then it would be 60 and then 90.
Yeah. So 0, positive 30, positive 60, positive. How about the orange ring?
Negative 30.
The yellow ring?
Negative 60.
The south celestial pole?
Negative 90 degrees.
Michaela, what is the total range of declinations that can exist on the celestial sphere? The complete range of declinations.
Between like from 0, so from negative 90 to 90, so it'd be 180.
Ah, beautiful. From negative 90 to positive 90 is your range of declinations. Now you and I are talking. See, you understand me. And I hope the rest of you are listening in on this convo. Okay, is Polaris a circumpolar star?
Yes.
It's the ultimate circumpolar star. It never rises or sets. And what's the declination of Polaris?
90 degrees positive.
Positive 90 degrees. That gives us our maximum. Michaela, what is the last star that is just barely circumpolar in our sky? The star that's just barely not circumpolar is the star that does what?
The horizon.
In which direction?
That is
North, south, east, or west?
north.
Right, because we're looking towards the north. Wait, shit, I'm not sharing my screen with you. Hold on. I don't want to lose this because Michaela's doing good here. Michaela, 83, F5, 83. Okay. Annotate. Michaela, the one that grazes your northern horizon, the one that grazes your northern horizon is the last circumpolar star, right?
Yes.
Now I'm going to ask the hard question. What is the declination of your northern horizon? Because that's the declination of the last circumpolar star. Let me try that again. Share screen, slide, picture 79. Michaela, can you tell me the declination of your northern horizon? That would be a ring that kind of, forgive my crude drawing, but it would look like this. It would graze the northern horizon and it would kind of come up here. That's what we need. We need the declination of your northern horizon. Anyone else is welcome to chime in if they're following us. Okay, Michaela, you're our only hope. How do we define declination again?
It was the degrees measured positive or negative from the celestial equator.
And the celestial equator is the entire red ring, right?
Yes.
So if I make a line here towards the northern horizon, and I make a line here towards the celestial equator, this should be the declination of your northern horizon. Can you tell me what that angle is?
30 degrees?
No.
Or the
30 degrees is 30 degrees is the blue ring, and it's clearly going above the blue ring. You may need to use the alpha, beta, gamma, delta game from our last class to answer this question.
Would it be 42 degrees?
Careful, Brandon. 42 degrees is the altitude of Polaris. You want to try that again?
Oh, it'd be negative 42. No.
False.
Yeah, it would be because it goes 360, right?
No. It's up from the celestial equator.
What?
48 degrees?
Say that again. Who is that?
Is it 48 degrees?
Yes, who said that?
Amber?
Amber, where are you?
Hello?
Oh, hi. Amber, you're awesome. Yes, this angle is positive 48 degrees. Yes. Way to go, kiddo. You got it. This was a real tough problem. One of the reasons why this problem is so hard is it's very difficult to simultaneously have the horizon system and the equatorial system in your mind. The horizon system measures degrees up from the horizon, but the equatorial is going north or south of the celestial equator. Keeping those straight in your local sky can be a challenge. I have more to say on that, but I want to move on because there's no time. Okay, what are the other, we've already done these two. What's question number 47, Brandon?
Let me just find it. 47, lost at C1.
Okay, class, I need to make an executive decision here. And here's what we're going to do. We have 5 problems to do every day, but I got started a little late because of my own failings. And then we've been going kind of slow because we needed to cover more material, sort of. Here's my plan. We are about to do question 47. Then we'll take a little pause before lecture starts to freshen up. And then the last 2 questions we will integrate into the lecture at the appropriate time. I will do them as sample problems. Is everyone cool with that plan? Do we like it? And
Yeah.
that'll give us a little 5-minute, 10-minute pause before class starts. So why don't we beast out question 47 real quick, and then we'll get to our lecture. Okay? Or then we'll take a little break. Okay, Brandon, let me get my, hold on.
Really quick, what was the answer for E? Because I think I missed it.
You didn't, Tess. I made another executive decision. I crossed off E and made it not due.
Okay.
Is that cool? Only because we're a little behind, so I'm trying to cut some corners here.
That's good. I just thought I missed it. I just want to make sure.
I'm glad we talked about it then. Okay, so Brandon, read us question 47, if you will.
Lost
at sea.
All right. During a vacation, you decide to take a solo boat trip. While contemplating the universe, you lose track of your location. Fortunately, you have some astronomical tables and instruments, as well as a UT clock. You thereby put together the following descriptions of your situation. It is the March equinox. The sun is on your meridian at an altitude of 75 degrees in the south. The UT clock reads 2200.
Okay. Class, to solve a lost at sea problem, we need to draw a diagram. First, I want you to take down your givens. These are your givens. And then I want you to try to make a diagram like so. First, we will draw in a line, and we will mark the midpoint of that line. Then we will draw the radius in like so, and we will make the best damn dome that money can buy. We're making a two-dimensional picture of your local sky. Here's the boat. The mast of the boat is pointing towards your zenith. Let's put north on the right-hand side. Let's put south on the left-hand side. And because I'm feeling especially artistic today, we'll put some blue waves underneath the boat. What an artist dies with me. Okay, now, what should we do? I'm stumped. That's about as much as I got. Our job is to find the altitude and the azimuth of this boat. Sorry. Dumb. That was a dumb thing I just said. Our job is to find the latitude and the longitude of this boat. Let's start with the latitude. Let's start with our givens. You should be able to put the sun on this diagram. Can someone tell me how to put the sun on this diagram?
Why don't you just go up 75 from south?
Very good.
75 degrees?
75 is like pretty high up there, right?
Yeah.
I'll leave a little 15-degree wedge. Sorry, that orange wasn't very visible. Let's try a better orange. That orange isn't very visible either. I wanted to use orange for the sun, you know? And that angle is 75 degrees, correct? I'll switch to red.
And then the spring equinox, right? We could put that on there.
No, hold on a second. This is a really important idea. Why are they telling us it's the spring equinox? This matters so much. Why tell us it's the spring equinox? What does that tell us?
Because it gives us the RA and the declination, right?
Of what?
Of the lot. Well,
Yeah.
well, no,
Right.
the what the declination would be the latitude, and then the rise ascent, or the
Hold on.
rate ascension.
Let's look at this picture here. Let's look at this picture. Why are they telling us it's the spring equinox? Where's the sun on the spring equinox? Can someone take a marker and point to where the sun is on the spring equinox? Yes. Was that you, Brandon?
Yeah.
I knew that because you had purple in your background. So hey, listen, I'm going to say something that sounds kind of weird, but I want you to listen to it carefully. On the spring equinox, the sun is on the spring equinox. On the spring equinox, the sun is on the spring equinox means many things at once. The spring equinox is a day, March 21st. The spring equinox is also a point on your sky where the celestial equator meets the ecliptic. The sun is on the celestial equator on the spring equinox. And the meaning of that is that they're telling us it's the spring equinox so that you know that this is the celestial equator. If I want to know where my latitude is, I need to remember the following rule. The altitude of Polaris is equal to my latitude. Can you guys tell me where to put Polaris on this diagram? Where would Polaris be?
It'd be 42 degrees north, right?
We're not lost at Rhode Island. We're lost at sea.
Oh, true.
Right? We are lost in Rhode Island, but in general, this problem does not necessarily assume the boat is located in Rhode Island.
So wouldn't Polaris kind of be on the other side of the zenith at 15 degrees, if that makes sense?
Not 15. Michaela, you're so close. You're so close. Could I remind you that the equator makes what kind of an angle with the North Pole?
90 degrees, right?
So rather than having it go 15 degrees, do you want to revise your statement, Michaela, or Brandon? Either one. Where should I go?
Well, it goes 75 degrees up north, right? Because wouldn't it be?
It would be
like symmetrical almost to the other side.
Can you just tell me where to put Polaris? Let me know where I should put it.
Like, hold on, go back up. Keep going. Wouldn't it be like stop at like? Wouldn't it be like?
It would not be here because that does not make a 90-degree angle.
It'd be 15 degrees above north.
That's what I wanted to hear. We've got to stay perpendicular to this. Do you see, Michaela? The North Celestial Pole has to make a 90-degree angle with the equator, right? And as Brandon said, it should be 15 degrees. What's our latitude here? Look for the box with the stars next to it, underneath the alpha, beta, gamma, delta game.
Oh, it'd be 15 degrees is your latitude.
Yeah, how did you know that?
Because that's the altitude of Polaris is your latitude.
Yes. So your latitude would be 90 minus 75 degrees. Okay, yes, it's 15 degrees, Brandon, but is it 15 degrees north or 15 degrees south? A full latitude has north and south included as well.
It'd be 15 degrees north.
How did you know it was north?
Because that's where Polaris is.
How did you know that was Polaris and not the South Celestial Pole? Gotcha, didn't I?
Yeah.
Does anyone know why it's north?
Because it falls north, because it's closer to the north than the south, and because it's the zenith, so it's on this side.
All they gave us in the problem was that the sun was at an altitude of 75 degrees in the south. I'm going to answer this one for you because I don't know if you'll be able to do it. In the northern hemisphere, the sun travels through the southern sky. So I'm going to say something that's as simple and as stupid as possible. If the sun is in the south, you are in the north. If the sun is in the north, you are in the south. Okay? Let me show you that with diagrams. Fudge. Sorry. Hold on. Astrometry. Let's find the sun's path from different perspectives. This is a north latitude, slide 51. Unfortunately, the sinister left-handed artists of the world have conspired to put north on the left-hand side. I am spiritually opposed to this, and I curse their names. They will die an evil death and not be admitted to Valhalla. Okay, but if we ignore that, if you're in the north, the celestial equator travels to the southern sky. If you're in the southern hemisphere, the celestial equator travels through your northern sky. So, sun is in the south, you are in the north. Sun is in the north, you are in the south. Remember that. 15 degrees north is the answer.
So it's always up. Okay.
Sorry, you guys are getting this a little quicker and faster than I would have liked. Longitude. Here's how we do longitude. Based on the position of the sun right now, can you tell me the local time based on where the sun is?
Will that be just the 22 right there for the UT? Or?
No, okay, here's how this works. UT clock is the clock at the prime meridian.
Oh.
And the prime meridian has a longitude of 0 degrees. Our local clock is clearly not 2200 hours. And I'll explain why. Brandon, what time in terms of AM or PM is 2200 hours?
That would be 10 p.m., right?
Would the sun be in your local sky at 10 p.m.?
No.
Hell no. So it's clearly not 2200 hours at this boat.
Yeah.
What's the local time based on where the sun is?
That'd be 10 a.m.
Nope. The sun is on your meridian. What time is the sun on your meridian?
Would it be noon?
That's right. And in military time, the local clock is 1200 hours. How many hours off are we? The hours from the prime meridian, how do I figure that out?
Would it be 10 hours?
Yeah. So it's 22 o'clock minus 12 o'clock equals 10 hours. In our last class, I tried to teach you how many degrees per hour the Earth rotates. How many degrees per hour does the Earth rotate?
15 degrees.
Let's multiply this by 15 degrees per hour. What do you get?
My calculator's dead.
Sorry?
My calculator was dead. I got to charge it. I'll save it.
If you use a Casio calculator, it never dies.
I had it in the dark.
Oh, I see. You can't. Can anyone do 10 times 15 in their head?
150.
Good. Okay, we're not done yet. This is the hardest part. Is it 150 degrees east longitude or 150 degrees west longitude?
Oh wait. Hold on.
Is Rhode Island east or west of the prime meridian? Are you guys getting zapped? Are you losing it?
Would it be west?
Yeah. How'd you know that? Who said that?
Megan?
Megan, how'd you figure that out, smarty pants?
Well, I just looked at my notes. And the longitude is 71 degrees west for Providence, Rhode Island. So I just kind of guessed.
You guessed right, but that, okay, listen. I know from my own, here's how I do the East versus West thing. Does anyone ever had a friend in England or London, or maybe you've traveled to Europe? Is it later or earlier in England than it is in Rhode Island?
It's later.
It's later by about 5 hours. So my rule of thumb goes like this, just based on personal experience. If England is later than your local time, you are west. If England is earlier than your local time, then you are east. And England is where the prime meridian is. Are we currently earlier or later than England in the current setup, comparing 22 versus 1200 hours? Is this boat earlier or later than England?
Earlier.
Yeah. So it's the same relationship as Rhode Island, which means Megan was kind of right, although I think it was a little bit of guessy on her part. We are 150 degrees west of England. But if you ever had to do this on an exam, if ever this was an exam question, then you'd use the rule of thumb. If England is later, I'm west. If England is earlier, I'm east. Listen, guys, we've only done 3 problems, but this stuff, it's some of the hardest stuff in the class. And you just barely learned it a few days ago. So try not to get too frustrated. It's tough stuff your first time around. Does everyone have the complete answer here? Okay. Here is my proposal to the class. We have now completed 3 of our 5 homework problems, and they were the hardest of the 3 homework problems. The other 2 homework problems, they're not so bad, but we can introduce them during the lecture. You know how every time I introduce a new formula, I give you a sample problem with that formula? I'll introduce the formula and I'll make the homework the sample problem, so we'll kind of do the homework and the lecture at the same time, the last 2. Everyone's cool with that plan, right? Okay. And that means we could give ourselves like a 7 to 8 minute break before we start lecture, just to kind of relax and refresh our minds. Would you like that as well? Just a brief pause? Okay. So let's get going around 12:10 or 12:15 at the very latest. Give yourselves a little 10-minute breather, and then we'll get to lecture. I'll be floating around. I'll be probably just drinking some iced tea, okay? All right, I'm going to pause the recording so we don't waste time during the recording. Breaks are dangerous. Once you start breaking, it's hard to stop. I thought that would be nice to kind of give ourselves a little refresher here before we begin our lecture. Normally I like to play my intro theme song, but I think I'm going to skip that today and just kind of get right down to business. We're going to learn a little bit today about the motion of the sun, the moon, and the history of astronomy. I'm hoping it'll be interesting. Let's begin by reviewing for our notes some concepts related to timekeeping. Today's lecture is going to feature a little bit of timekeeping as well. Ooh, Amber's outside now too. Damn it, I want to teach outside. I can't do that though, because I need the whiteboard and stuff. Okay, let's go to my share screen for a moment. Oh, here comes Zach's back. How's it going, bud?
Doing good. Just making some food.
Nice. Are you actually grilling?
Yeah.
Damn. That looks like fun. I feel like I'm at your own personal barbecue giving you a lecture. Maybe this quarantine thing isn't so bad after all.
Yeah. Should do it outside next class.
Well, I live downtown, so there'd be some crackheads running around the background. I don't think it would be conducive to learning, but who knows? I do have access to a rooftop. I'd have to figure out the note thing. I think the note thing is, my dad watched one of my lectures and he said, hey, why don't you just, you know, give them the slides or give them the text write-up. I think me writing it down and then you writing it down is kind of good. I'm not sure about that, but I think so. Anyways, I'm going with it. So let's begin by a little bit of timekeeping here on that note. Okay. Some notes on timekeeping. You keep, or I guess I could say we keep, but astronomers have their own kind of ideas about these things. You keep what is called solar time. Solar time is time by the sun. And yes, as you will discover in a few moments, it is possible to keep a different type of time. Sidereal time is by the stars. So let's put that in brackets. Versus sidereal time, which is time by the stars. It's possible to do that. And in fact, you're going to learn how. When it comes to solar time, there are two types of solar time. There is something called apparent solar time. Apparent solar time is time keeping by a sundial. And I would like to contrast that with something called mean solar time. Mean solar time is time by a watch. Let's say a mechanical watch. Let's add that. You guys might actually be surprised to discover that there is a difference between time by a sundial and time by a mechanical watch. They're not exactly the same. Okay, let's go ahead and let's look at a diagram together. I'm just gonna pull back. I wanna get my chair in here so I can rest. Let's go to my lecture show on astrometry, F5. And let's go to slide 3 or 4 or 5, and let's start by looking at that nice picture I had of a sundial. Imagine keeping time by a sundial, and imagine how apparent solar time works. Let's say it's the spring equinox when the sun is on the celestial equator. You'd like to make it so that, I'll use yellow for the sun. When the sun is here at noon, oh, sorry, let me try that again. When the sun is crossing your meridian, you'd like that to be noon o'clock. When the sun is at its lowest point underneath your horizon, you'd like that to be midnight o'clock. And the ancient Babylonians or the Egyptians, some ancient people, Sumerians, probably Babylonians, they divided the rotation of the sky into 24 parts, each part which was 15 degrees. Ancient Babylonians probably kept time by a sundial because as far as we know, there were no mechanical watches at that time. They made it so that it was 6 a.m. anytime the sun was on the eastern horizon. When the sun was on the meridian, they made that noon. And when the sun was setting on the western horizon, it was 6 p.m. And halfway between that would be midnight. And that's basically what happens if you keep time by a sundial, because you're basically just following the shadow of a stick. When the sun is at the, this stick is called the gnomon. It's one of my favorite words in the English language. Let's write that down. This is called gnomon, like phenomena, okay? A gnomon is the stick that points towards Polaris. And if you point the stick towards the North Celestial Pole, when the sun's on your meridian, the sun will be located in that direction. and the shadow of the stick will point in that direction. And that's what you want to be 12 noon. When the sun is on the eastern horizon, let's see, rising in the east, setting in the west, the sun will be in this direction, and the shadow of the stick will point to 6 a.m. there. And when the sun is in the west, the sun will be setting over there, and the shadow of the stick will point in that direction. Now, why is this different from a mechanical watch? Because each day, the rate that the sun travels through the sky changes. And this is going to be a little bit of a hard pill to swallow. So let me start by showing you a kind of cool photograph that explains this. This is a famous picture of a shape known as the analemma. Let me type that in here. This is a legendary figure called the analemma. I think I spelled that right. In this photograph, this is a photograph, some intrepid astronomer has decided to take a picture of the sun at 12 noon for every 2 weeks for an entire year. Well, let's see, is it 1, 2, 3, 4, 5, 6, 7, 8, 16, 24, yeah. So they've basically taken a picture maybe every 2 weeks at exactly noon. If they were keeping time by a sundial, the sun would have to be directly on the meridian. But what you're going to notice is at noon o'clock, the sun is, the meridian line, let me show you where the meridian line here. This is a little bit weird because in a photograph, you're taking the three-dimensional sky and you're flattening it. But the meridian line probably goes just like this, right through the center of the figure 8. And what you're going to notice is that on any given day, at mechanical clock, noon o'clock, the sun can be as much as 20 minutes later than the meridian or 20 minutes before the meridian. And that's a bit strange. By the way, can you guys see that they left the shutter open on 3 particular days? Let's start with my first arrow. The first arrow that you see here, what day is that? Can you tell me? What day is this? They're pointing their camera towards the meridian, and they leave the shutter open and watch the path of the sun as it moves through the sky. What day is this here? What day is this? What day is this?
The top one be the summer solstice?
Good. This middle one?
Would that be the fall equinox?
Or the spring, either one. And how about this one?
And then that would be the winter solstice.
Very good. Okay. They left the shutter open so you can see the path of the sun. Now, in this middle point at the spring equinox, you'll notice the sun is pretty much on your meridian at noon. But on any other day, the sun can be as much as 20 minutes ahead or 20 minutes behind the meridian. And that's kind of complicated, but it has to do with the fact that Earth's orbit is not a perfect circle. So when Earth is close to the sun, it moves a little faster. And when it's farther from the sun, it moves a little slower. That changes the rate that the sun moves through the sky. Now, if you were keeping time by a sundial, you would just kind of notice that the sun was at noon at your meridian. But what you would discover is that if you invented a mechanical watch, the rate that the sun moves through the sky was different. And that's not helpful for an agricultural society that wants to have, or a mechanized society that wants to have factories and worker shifts and things. It wouldn't be good if you paid your workers by the hour, but some days hours were longer than others. People would tend to resent that. So what people did is they decided to keep something called mean solar time. It's a little bit complicated to explain, but they calculated the average rate that the sun moves throughout the sky, and they based the clock on the sun's average motion. So in other words, every day when it's noon, are we at noon yet? We passed noon, right? What time is it? It's now noon 28. So 28 minutes ago when we were hanging out, it was noon. And you would expect the sun to be exactly at your meridian, but in fact, the sun could have been either 20 minutes ahead of our meridian or 20 minutes behind our meridian. In the olden days, everyone kept mean solar time, and they would have their own local clock or clock maker He was probably a Swiss guy who had some Big Ben-like clock in the town square. He would calculate the rotation of the sun, and he would calculate and wind up the clocks, and everyone would set their mechanical watch to his. There's still people whose job it is to do this, except it's more universal now. Here's the issue with that. In the olden times, when most people stayed in their village, it was okay to keep your local solar time because you didn't travel too many degrees of longitude on your horse and buggy. However, I'm trying to share my screen here. In the 1800s, you'll remember that the United States began expanding their modes of travel using railroads. And when they devised the transcontinental railroad system, let me scroll ahead here. People began traveling many degrees of longitude on trains traveling from places like New York all the way out to Los Angeles. And that covers a significant amount of longitude. Obviously, if you have a mean solar time in New York, that's not the same as the mean solar time in Chicago, the mean solar time in Denver, or the mean solar time in Los Angeles. And originally, when people would travel across the United States, they would have these maps of departures and arrivals that would say, you're leaving the train station at Rhode Island, 3 o'clock. You're arriving in Chicago at Rhode Island, 8 o'clock. But that's going to be Chicago, 3 o'clock. And it started to get so fucking confusing because you had all these different time zones that eventually the railroad companies were the first people to create something called standard time. They decided that they were going to break the United States up into bands of 1 hour or 15-degree increments. And there would be an Eastern Standard Time, Central Standard Time, Mountain Standard Time, and Pacific Standard Time, something like that, right? And these standard times would each keep the mean solar time of some central city. Like, for instance, Eastern Standard Time keeps the mean solar time of Philadelphia. So we're actually not keeping mean solar time for Rhode Island, we're keeping it for Philadelphia. Eventually, the rest of the world got on board, and we divided the entire world up into 24 time zones. You'll notice the boundaries of some of them are political, and not everybody conforms to what's known as universal time, okay? In fact, we now keep the mean solar time. Universal time is the mean solar time of Greenwich, England. So if you go to the prime meridian, if you go to the Royal Greenwich Observatory, UT 0 hours is midnight at the prime meridian, and everybody else is offset by some time zone. This can get kind of confusing, so let's take some notes on it. So when we keep Eastern Standard Time, that's the mean solar time of, well, technically, I think the central city for Eastern Standard Time is Philadelphia, but don't quote me on that. Just write it down as if it was true. I believe Philadelphia is in the middle of the Eastern Standard Time zone band. However, it's possible to have what's known as universal time. Universal time keeps the mean solar time of Greenwich, England. In other words, they sometimes call it UT. They sometimes call it GMT. And if any of you have been in the military, I think they call it Zulu time. That's what they refer to it. Uncle Sam refers to it as Zulu time. Now, if you're a BBC fan like I am and you hear Owen Bennett-Jones on the radio, he'll say, it's 1300 hours GMT and you're listening to the BBC. And he's telling you what the local mean solar time is at Bush House in London, which is pretty much at the prime meridian. Now, Eastern Standard Time is usually UT minus 5 hours. But during daylight savings time, we change it to UT minus 4 hours. That's Eastern Daylight Time. We'll get into that later on in our labs today. In other words, you keep time by the sun. I'd like to have a couple of definitions here. We talked a little bit about the meridian, right? What's the meridian? Oops, sorry, I didn't share my screen. Where's the Zoom? Share the Zoom. Share the screen. F5. Got to click, then I have to hit F5, then 79. It's a whole damn operation. Okay. I need to move you guys over here. Where's the meridian in this picture? Talk to me. Don't leave me alone. Where's the meridian?
Is it the red line?
False. That's the celestial equator.
Oh.
Do better.
It's the white arch.
Michaela, more, yes, yes. It's the white arch that's doing what?
That's going from north to south.
Very good. Okay, so Michaela knows that the meridian starts north, comes up to your zenith, and goes south, right? All right, the reason why I needed you to remember that, Michaela, is I'm about to throw a little chaos into your life. There are two meridians. The one that's above you, the one that we've been talking about so far, is referred to by astronomers as the zenith. I shouldn't use red here. I should, because it's going to confuse you with the celestial equator. Let's use freaking blue, dark blue. This is known technically as the zenith meridian, okay? But Michaela and friends, can you see that there's kind of like an anti-meridian? There's another meridian that starts north. It's not in your local sky. It's like underneath your feet, and it goes like this. I'm going to define that. That is known as the nadir meridian. Okay, why do I call that one the nadir meridian? Do you guys see this point that the yellow arrow is pointing to right here? The point in your sky that's opposite this, this is technically not in your sky. If you could drill a hole through the earth, down through your feet, down through China, and out the other side of the sky, that lowest point is known as the nadir. It's an old-fashioned term. Class, when the sun is on the zenith meridian here, what time is it? Work with me. The sun is on your zenith meridian. What time is it?
Noon.
Very good. It's noon. What would that be in a 2400 clock? Jesus, I can't talk. A 24-hour clock, that would be 1200 hours, correct? Correct. What time is it when the sun crosses your nadir meridian? Amber, want to try that?
Midnight.
Very good. Amber, it's midnight when the sun's at your nadir meridian. That's how we do, and that would be 100 hours, right? On a 24-hour clock. So
Yeah.
I want you guys to never forget this. You keep time by the sun, and you start your day there. Your day starts at midnight when the sun crosses the nadir meridian. That's how time works. Welcome to the world, okay? You know, there are two types of day. Do you guys remember what they are? What are the two types of day? Let's take notes. You guys did this during your homework today, so you should remember that there are two types of day. There is a solar day and that's 2,400 hours. That goes from noon to noon, or it's when the sun goes from 1 nadir meridian back to the nadir meridian. I guess it's not noon to noon. It's really midnight to midnight, right? Does that make sense? You guys understand why I said midnight to midnight, right? There's also a sidereal day. How long is the sidereal day?
23 hours and 56 minutes.
What does that represent? Sorry, I wrote that stuff kind of badly. This looks like crap, so I'm going to fix it. The solar day goes from midnight back to midnight. It goes from 1 nadir meridian back to the nadir meridian. I just cleaned up my writing, that's all. What makes the sidereal day different than the solar day? Brandon, can you tell us?
I can't believe I'm drawing a blank right now.
Would this help?
Oh,
Feel free to.
It's not at noon, right?
What is it?
The Earth is not. Oh my God.
Is the Earth ever at noon?
No.
That doesn't make any sense, right?
Yeah.
If it's noon in China, it's not noon in Rhode Island.
Yeah.
The Earth is never at noon. The Earth has a multiplicity of times everywhere around the globe. Sorry, I kind of have to take you to task a little bit. Can anyone jump in and help Brandon? Don't let him do it all at once. Michaela, Zach, Yanita, Ian, Dennis, Tess, I know you're all dying to contribute to this conversation. What's the difference between the sidereal day and the solar day?
It has a true 360-degree spin.
Booyah, Zach, that's what I wanted to hear. That's exactly what the hell I wanted to hear. The sidereal day represents the true 360-degree spin of Earth. The sidereal day represents the time for a single star to rotate around the sky. Unlike the solar day, this is the time for a star to go from your zenith meridian back to your zenith meridian. I want to elaborate on that for just a moment. There's a famous star in the sky called, what's the famous star? Let's take a star, the brightest star in the sky. It's Sirius, okay? Did you know that if this arrow points towards the star Sirius, capitalize it, that this arrow up here would also point towards the star Sirius? In other words, what I'm trying to tell you is Sirius is located in that direction, and in that direction, and in that direction, and in that direction. Does anyone understand that? That's something that could potentially be confusing. The sun is only in this direction, but how can the star Sirius be in the direction of all of these arrows, oops, at the same time? How can this arrow point to Sirius, and this arrow also points to Sirius, and this arrow also points to Sirius? How is that possible?
Is it because it's bigger than the sun?
Not because the star is bigger. Isn't it possible for me to kind of create a whiteboard here? I haven't done this feature. I did it once. I can share screen, and I can do a whiteboard. Cool. Let's say, let me use my drawing features, okay? Let's say that's, I'm still working this out, guys. Bear with me. Oh, there's a star feature. Fuck yeah. Boom. Let's say that's Sirius, okay? Do you see that? The distance to Sirius is really fucking far away, like super far away. Compared to that, the orbit of Earth, the orbit of Earth looks like this. Let me draw the orbit of Earth. Oop. Okay. Oh, wait. That's the orbit of Earth. And the sun is in the center of that. So what I'm trying to say is, it kind of doesn't matter the Earth's, where it is around the sun. The circle of Earth's orbit is so freaking small compared to the stars that any arrow that points vaguely in that direction is pointing towards the star Sirius. That is why in this diagram here, this is a thing that you have to understand from your astronomy class. Look at this diagram here, F520. In this diagram, both, sorry. Bear with me, kids. In this diagram here, this arrow points towards Polaris, and this arrow points towards Polaris. Because Polaris is so far away compared to this little circle of Earth's orbit that any arrow that points in a parallel direction will point towards Polaris. Does that make sense? It's because the stars are so far away. In other words, with that in mind, I'm trying to make a point that if a star, and this isn't true for the sun because the sun is only one astronomical unit away. This arrow points towards the sun. This arrow does not point towards the sun. But both of those arrows point towards, paradoxically, the same star. Do you get it? For this reason, a sidereal day is a true 360-degree spin, and it's the time for a star to circle the sky. And let's make stupider definitions. Can we get stupid for a second? I want to make this real dumb. The solar day tracks the time for the sun to orbit the sky. The sidereal day tracks the time for some random star, any star you'd like, to orbit the sky. Does that make a little bit of sense to you guys now? Can you guys follow that idea? What if I told you that astronomers don't keep solar time? They don't care about the sun. They care about stars. It's possible to do this. In fact, astronomers have a little joke. Now, anytime there's a little joke in astronomy, it's usually not that funny, but just go with me. Here's the joke. The sun rises four minutes early each day. But does anyone understand that joke?
Because you're going off a sidereal
Sidereal time, yeah. You're basing your clock on a 23 hour and 56 minute day. They're keeping the rotation of Earth. Another way to say this is this. The sun travels 1 degree, which is equal to 4 minutes eastward along the ecliptic each day. Each day, the sun is drifting 1 degree, which is 4 minutes along the stars of the ecliptic. These are things that you wouldn't think of yourself. I have to teach this to you, and someone had to teach it to me. I guess way back in the day, somebody figured all this out. They were smart people. I'm here to tell you that astronomers do not keep solar time. They keep a different type of time, sidereal time. Now, if we're going to choose sidereal time, we have to pick some random star to orbit the sky, and we'll keep time by that object. Which star do you think we chose? Take a guess.
Polaris?
That actually wouldn't make sense because Polaris is one of the few stars that doesn't really orbit the sky. I mean, it barely does, but I was honestly hoping you would say that so we could talk about that. Do you agree that, like, Polaris is like here, right? You're not even seeing my screen. Okay, I'm losing my mouse. I'm losing my mind. Share screen. Exit. So many buttons. Slide 81. You'll notice here that Polaris rotates the sky, but not a lot, right? Like, it's barely doing a little orbit around the north celestial pole, which is here. Polaris probably wouldn't be the best object. We'd want to pick one that was closer to the celestial equator. In fact, I've got an idea. What if we didn't pick a star at all? What if instead of picking a star, what if we picked the spring equinox to be our artificial star? And we'll keep time by the spring equinox instead of any one particular star. That will be like fair because then we aren't biasing it towards any one particular star, which might drift. We'll do it by the spring equinox. I'd like to remind the class that the spring equinox is actually a point on your sky. In slide 34, you can see that the spring equinox is where the celestial equator and the ecliptic meet. And that's cool. But on the next diagram, you'll notice that the spring equinox is actually a point on your sky, somewhere below the constellation Pisces. That's how we're going to keep sidereal time. Okay, ready to learn something that's really confusing? Hang on to your hats, kids. Introducing an alternative to solar time. It's known as local sidereal time. Local sidereal time is time by the spring equinox. I'm going to have to make a few new definitions, though. To understand local sidereal time, we're going to need to make a two-dimensional drawing. Follow along with me. We're going to leave some headroom. Make a line that's about 8 centimeters long on your page or so. I'm going to draw the radius here. I'm going to draw the best damn dome that money can buy. Or at least the best that I can draw. It's not perfect, but it's okay. Okay. This time, we're going to follow the rotation of stars. This is very important. We're going to make an east to west diagram this time, with east on the left. The observer stands in the center of the field. This is no longer the observer's zenith. This is the observer's meridian. The reason why is not every star will cross your zenith. Stars on the celestial equator will only get as high as 48 degrees. I want you to imagine stars rotating from the east to the west, right? So every star is rotating in this direction. And I'm going to put a star about 15 degrees west of the meridian. Class, if that angle is 15 degrees, can you tell me how many hours ago did that star cross my meridian? Actually, I'm going to try to make 15 degrees a little more precise here.
Would it be 4 hours?
Not 4 hours.
Is it 1 hour? 15 degrees is 1 hour, right?
Yeah, exactly. That was my point. This is probably 15 degrees here. I'm going to try and make that a little better. There's my star. So who said that? Who got the 1 hour? Was that Brandon?
Yes.
Very good, Brandon. 15 degrees is equal to 1 hour. So I could either keep degrees from the meridian or I could keep hours from the meridian. Considering that the sky is a clock, I'm going to keep hours. Let me introduce a new vocabulary term to you all. It's called the hour angle, or HA. The hour angle is defined as the time since the meridian. Every star in the sky has an hour angle. You just count up how many hours since it crossed your meridian, and that's the hour angle. In the case of my blue star, the hour angle is 1 hour. Okay, suppose, students, that I took a green marker and I tried to locate the point known as the spring equinox on this diagram. Let's say on this particular night, at this particular moment in time, the spring equinox was found about there. Class, can you guesstimate for me the hour angle of the spring equinox in this diagram? What would you say the hour angle of the spring equinox is?
Looks about 15 degrees, so it'd be about 1 hour.
No, the blue star is 1 hour from the meridian. What is the hour?
Oh, from the meridian. I got you. So it looks about 75 degrees.
But if you did it in hours, how many hours would that be? Here's a hint, Dennis. How many hours does it take to go from the meridian to the west? It's a quarter turn around the sky. How many hours is that?
Six.
So the hour angle of that X would be what?
18.
Try again.
18 hours.
Nope. 18 hours would be past 12. From the meridian. From the meridian, it's clearly less than 6. Is 18 more than 6 or is 18 less than 6? 18 is more than 6.
18's more than 6, yeah.
You just told me from there to there is 6, right? So try again.
Yeah. So 3.
3 would be in the middle.
Wait, sorry, I'm missing something. So that would be 1. Then if you split that, that would be 2. So it'd be 3, right?
You know what I think is happening? You're getting mixed up a 12-hour clock and a 24-hour clock. Remember
that's what I think I'm doing. Yeah.
So remember the sky. Watch this. Let me get my pointer stick out. Dennis, I know exactly what's going on, and this is instructive. Okay.
Yeah.
Dennis, you're used to thinking of a clock that goes around in 12 hours, but that's because you keep a lame-ass fucking solar clock. I'm asking you to be bold and to keep a cool-ass 24-hour clock. Dennis, if it's 24 hours around the whole circle, how many hours is it to do a half circle?
12.
How many hours is it to do a quarter circle?
2.
Wait, from here to here? You just said half a circle is 12, and now you're telling me a quarter circle is 2?
3. 3, 6, 9, 12 would be
I'm
a
asking
quarter.
you to go. I don't want you to go to 12. I want you to go to the 24. Dude.
So 6. It was 6, 12, 18, 24 would be 25%.
Fine. Now you're with me. 6 hours, right?
Yeah.
So if from meridian to west is 6 hours, what's the hour angle of this bad boy right there?
So so it would be 4.
4,
correct?
or maybe even 5, right?
I didn't hear that. That came in staticky.
Sure. Hold on a sec. Let me get my calculator. Dennis, 4 hours would be a reasonable guess. I thought you were going to say 5 hours. See, originally, I think you were trying to say that you thought this angle was 15 degrees, right?
I'm looking at it as a 15-degree angle, yeah.
Well, then this would be 75 degrees, right?
Yeah.
How many hours is 75 degrees?
Um, 5.
So, Dennis, I'm going to ask it one more time. What would you say the hour angle of the spring equinox is in this diagram?
5 hours.
Very good. What you just did there is you just told me the hour angle of the spring equinox. Astronomers define this as local sidereal time. Watch me now. I want to do it in green, but I hope the contrast is good enough. Hold on. That green sucks. Okay. LST stands for local sidereal time. That's what we're here to learn. Let me define local sidereal time in black so that the contrast is better. The local sidereal time is defined as the hour angle of the spring equinox. You cool? What? This is confusing your first time around, kids. There's no two ways about it. Okay, next up. I need a hand here. It is possible to put right ascension onto this diagram. Do you guys remember what right ascension is? It's a coordinate of the stars measured in hours. Megan, you've been our definition guru. Want to look up the definition of right ascension for us?
It's the hour and then minutes of a star measured eastward counterclockwise from the spring equinox.
Megan, I'm going to rewrite the short version of that answer down here.
Okay.
Right ascension is just the hours east of the spring equinox, okay? That's the short and dirty version. Hours east of the spring equinox. Megan, would you agree that this star, being a star in our sky, must have some right ascension? Does every star in the sky have a right ascension?
Sure, yeah.
Okay, just like every point on Earth has a longitude, kind of. How would I represent the right ascension on this diagram then? If it's hours east of the spring equinox, if the spring equinox is there, which direction is east in outer space?
I'm not sure.
I bet someone remembers because it was one of the things we talked about at the beginning of lecture. Dennis, do you remember? Who was I talking to? How do we define east in space? Look at your class.
What was it? Was it north?
No, east can't be north any more than up can be down or black can
Oh
be
wait,
white.
sorry, I didn't hear the question. My bad.
Which direction is eastward in space? Look in your notes on the first lecture under the orbit of Earth.
Isn't it like counterclockwise?
Yeah, who said, was that you, Michaela?
Yes.
You are a badass. I love it. Counterclockwise is east. So Michaela, since you're such a badass, if hours east of the spring equinox is right ascension, show me how to draw a right ascension on this diagram. Count. Where should I go?
East, you'd go left
From what?
from the meridian.
Fuck no. That's not how we define right ascension. Right ascension isn't hours east of the meridian.
So then from west all the way over?
It's not hours west of the, it's not hours east of west. That's not how we, what's the definition of right ascension?
Was hours east of the spring equinox.
So tell me what to do with my magic marker here.
Oh, so go from the spring equinox to east or vice versa.
Eastward to the star, right? Based on the drawings that you see here, can you estimate the right ascension of that blue star for me? Here's a
5
hint.
hours.
Huh?
What? 4 hours?
Very good. How did you do that? Explain that to everyone.
Because if it's 5 hours from the spring equinox to the meridian, you subtract the 1, which
Of the
is
star.
not where the red is. Yeah.
You just derived on your own a critical formula, which is kind of the definition of local sidereal time. Are you ready to receive the wisdom? Here's the formula that you need for our homework problem. I'll write it in fun colors. My nickname for this formula is Ha equals list minus Ra. It looks like this. Ha, the hour angle, is equal to the local sidereal time minus the right ascension. That is a key formula in this class, and you just derived it intuitively. Let's look at what Michaela did. She took the LST, 5 hours, subtracted the right ascension, 4 hours, to get the hour angle of the star, 1 hour. Okay, class, you've done a lot. It's time to try our homework problem. But the homework problem that we're about to try is not the fourth homework problem. It's the fifth homework problem. Now, I've got a certain method to my madness. I decided to introduce this formula first while you were fresh because it's very hard. Do you guys have all this down? Because I need to erase it in a second. Michaela, are you still writing? No? Megan, Amber, Zach, you cool?
I'm good.
All right. Anyone mind if I erase? Then I'm going to do that. Okay. What was the number of our last homework problem? Let's return to the homework for a minute. Let's do one more homework problem. Chapter S1. This is our sample problem where we use the formula. Okay, or I could look it up. Not like I've got anything else to do.
It's 53.
Okay, thank you. Chapter S153. Can you read that for me? What's the title?
It's just the equation is the title. So HA equals LST minus RA.
Very good. Okay, and what does it say to do?
It says, hold on. It is 4 p.m. on the March equinox. What is the local side real time?
Let's draw a picture of this. We have to make another east to west diagram to solve these problems. Over here, I'm going to make a short diagram of the local sky. Okay? This is our meridian. What are they telling us if they're telling us it's 4 p.m.? Does anyone know what AM and PM stand for? No?
Is it after midnight and past midnight?
No. AM is anti-meridian. Can we get some, would you mind turn the air code to like 70? I'm sweating like a pig at a Hawaiian luau, okay? AM is anti-meridian. PM means post-meridian. That's where AM and PM come from. They're telling you whether something is before the meridian or something is after the meridian. But what is the something? What is 4 hours past the meridian? If it's 4 p.m. Oh, you folks is not awake. I think that sunshine's rotting your brain, Zach and Amber. What's
8 p.m.?
Wait, 4 p.m. is not 8 p.m. 4 p.m. is 4 p.m.
No, 4 hours past 4 p.m.
Wait, 4 hours past 4 p.m. 4
Isn't that-
hours past the meridian.
Oh, all right.
What, Dennis, is 4 hours past the meridian if it's 4 p.m.? What the hell are we tracking with a clock anyways? I'm getting confused. I thought I understood clocks and now I realize I don't. What is 4 hours past the meridian? What is it?
Isn't it 4 o'clock?
4 o'clock.
4 o'clock tells you what?
That it's 4 hours past the meridian?
What is it? What is 4 hours past the meridian? You're saying it is 4 hours past the meridian, but what is it?
The time?
No, the time is 4 p.m. The
That's
time is telling you what? Who said it? Where? Who are you? Where are you?
Spring equinox.
No. Talk who's
The sun?
someone else. Megan, say it one more time, loud and proud.
The sun.
The fucking sun. That is what you track when you say 4 p.m. It's solar time. You're keeping the time of the sun through your sky. The sun. Megan, where do I put the sun on my diagram if it is 4 hours past meridian? Let's say this is east and let's say that's west. Where's the sun? Tell me to draw it.
Probably, well, can you like put your marker where the meridian is?
Okay. Wait, let's use red for the sun. Okay, so what do I do?
So go right. Keep going. Right there, maybe?
Yeah, if this is 6 hours, then 3 would be like half, right?
Yeah.
So a little more than 3, right? Maybe like, there. Is that the sun? Megan?
Sure, yeah.
Guess so, right?
Mhm.
But there's just one problem. If this is 4 hours, the time is the hour angle of the sun. But the local sidereal time is what? Definition of local sidereal time. Regurgitate now.
It would be the time by the spring equinox.
Or find the one with the stars next to it and repeat that one.
Wait, what am I looking for?
The definition of local sidereal time I put in a box and I put 2 stars next to it so you could find it quickly.
It's the time for a star to orbit the sky, or the true 360 spin of the Earth, or 23 hours and 56 minutes.
That's fine, but it's not the technical definition of LST. I put a box around it and I put a star next to it. 2 stars, in fact. What is the definition of local sidereal time?
Is it the 8th day of the spring equinox?
That's right. It's the hour angle of the spring equinox. The problem as I see it goes like this, class. You currently know the hour angle of the sun, 4 hours. But what you really need is the hour angle of the spring equinox. So wait for it. I'm about to ask you a profound question. Where is the spring equinox on the spring equinox? Shoot, that didn't make any sense.
Isn't it with the sun?
Oh, fuck yeah. On the spring equinox, the sun is, who said that? Where are you? Amber, you rule. I did not expect anyone to get that. To be honest, Amber, I was just trying to confuse you all. I gave up on teaching a long time ago. Now I just go for confusion. But unfortunately, I could not confuse Amber. She's too good for me. She knew that on the spring equinox, the sun is on the spring equinox. Okay, so what's the answer then? If the spring equinox is here, what is the local sidereal time, Amber?
4 p.m. on the spring equinox.
We don't use AM and PM for time, for sidereal time. We keep a 24-hour clock. It's the hour angle of the spring equinox.
1600?
So the LST is what?
Is it 1600?
Fuck no. That's what I'm talking about. Wrong. There's no AM or PM. If the spring equinox is here, did it cross your meridian 16 hours ago? I think
It's
not.
16 hours or yeah, 16 hours or.
Okay, I can see what's going on. You know why you guys are getting confused? We keep solar time midnight when the sun crosses the nadir meridian. Hold on, I'm gonna need a picture for this because none of you are gonna follow me otherwise. Just a sec, you're gonna need a picture. You're gonna need this picture. We keep solar time, listen to me carefully, when the sun is 0 o'clock, that's when the sun is down here. But for sidereal time, we start 0 o'clock up here when the sun is at the zenith meridian. That's why you keep saying 1600 hours, because you're trying to say it's 1600 hours from the nadir meridian. But that ain't what's going on here. You're keeping sidereal time. Sidereal time starts 0 o'clock when the spring equinox is at your meridian. So if LST is the hour angle of the spring equinox, what is the LST?
4 hours.
4 hours, Amber. Not 4 p.m., 4 hours. Now you're with me. How are we going to prove it? We will say this. This is what they, sometimes when they give you an advanced problem and the professor or the writer doesn't feel like explaining it, he says, or she says, 400 hours by inspection. In other words, it means I just looked at the diagram and I'm Amber and I'm so smart that I just knew it was 4 hours. That's how we answered that question. By inspection of the diagram. Wow, that was a lot. I understand. Okay, read me question B, please. Brandon,
yeah, I guess I'll do it again. The local sidereal time is 19 hours and 30 minutes. When will Vega cross your meridian?
Okay, class, can I erase part A? Because I'm going to need the diagram again. Okay. This is a new problem. In part B, the sun and the spring equinox are no longer there again, okay? They're somewhere new. And they gave us what? They gave us the, say the givens again, Brendan?
The sidereal time is 19 hours and 30 minutes. When will Vega cross your meridian?
Okay, to do this, we need to know the right ascension of Vega. I happen to have the right ascension of Vega memorized. The right ascension of Vega is, I believe, 18 hours and 35 minutes, okay? Now, it wants to know when will Vega cross the meridian next. That means we have to find the hour angle of Vega. The hour angle will tell us where Vega is on the bloody sky. We're going to now employ the formula, and I want you to watch me carefully because it's easy to mess this up. I'm going to attempt to take the LST and subtract the RA to find the hour angle. I'll do it down here. It's important that we stack the times vertically. So HA is equal to the LST, 1930, minus the right ascension, 1835. Does anyone know how to do that? The Babylonians invented time as a sexagesimal system. That's a 60-base system. You can't punch that into your calculator quite so easy. How do I subtract that?
Would it be 1 hour and 5 minutes?
Careful. There's two different ways to do this. Can I show you my way? You know that song, Gotta Keep Them Separated? For hours and minutes, you gotta keep them separated, okay? I subtract them brutally with negatives and positives, and then I try to glue them back together. My method would be to do this. Brandon, what is 30 minus 35?
That'd be 5.
Say that?
0.5 seconds?
Nope.
5 seconds. No, 5 minutes.
Negative 0.5, right?
Yes.
What's 19 minus 18?
That'd be negative, no, positive 1. Okay.
What do you get if you take 1 hour and you subtract 5 minutes?
It's 55 minutes, right?
But there's one problem with this answer. They want to know when Vega crosses next, but the hour angle is time since the meridian. That's 55 minutes ago. So when will Vega cross next, my lovelies? Vega is currently here. 55 minutes past your meridian. When will Vega cross the meridian next?
Would you just add the 19 hours and 30 minutes plus
Nope. How long does it take for Vega to orbit the sky?
18 hours and 35 minutes.
False. How long does it take Vega to orbit the sky? How long does it take the sky to do a complete rotation?
$23 hours and 56 minutes.
Technically, you are correct, but let's just keep it simple because this is already complicated. Let's pretend it's 24 hours just for fun, okay? But you are right. It's 23:56, but fuck that, okay? Say 24. In a 24-hour clock, if Vega crossed 55 minutes ago, when will it cross next?
You subtract 24 hours by 55.
Yes, and what do you get?
23:05.
23 hours and 5 minutes is the answer to part B. That's pretty nuts. Okay. In the interest of time, you were originally supposed to solve problems A, B, and C, but I want to do a couple more things before we break. So can we just say that will be the completion of that problem and we'll leave it behind? So just parts A and B were all that's required. You got that, Tess? We're not missing anything, okay? I'm going to give you your full 5 points just for those two parts because you had to think hard enough just to do that. All right. Does everyone have that down? That's okay. I'm going to erase. Any objections? Local sidereal time is some of the toughest stuff you're going to learn in this class. It's unfortunate that it had to come on lecture 3, but this is the right time to do it. But I can understand that that was probably confusing as all hell. Unfortunately, it's also scary to learn to swim by just jumping into the deep end of the pool, but that's also how you learn to swim. I throw you in, I watch you flail, and I save you from drowning. And eventually, you'll learn to swim on your own. So try not to get too worried if that was confusing. It's supposed to be confusing, okay? That's what you paid for. We'll go over more examples at the appropriate time. Meanwhile, before we get to say 1:30 and we take a pause, let's squeeze like 1 or 2 more mini modules in, just a couple of 5-minute things before we stop. Let me go back to my lecture and let me try to confuse you some more. You just learned about sidereal time, and it was a jammy good time. What if I told you not only were there 2 types of days, there were 2 types of months as well? But this is going to require us to kind of learn our phases of the moon. So let's do something fun, and let's learn about lunar phases. In my first lecture, I should have that. By the way, our lecture today, our lab today is going to be on eclipse prediction. That ought to be fun / confusing. This slideshow has my lecture on the phases of the moon. Believe it or not, guys, despite being an astronomy student back in the day, I didn't learn my phases of the moon until graduate school. And I didn't learn it from a professor, but a fellow graduate student showed me a cool way to learn the phases of the moon. I don't know if you guys know this, but there are 8 lunar phases: new moon, waxing crescent, first quarter, waning waxing gibbous, full moon, waning gibbous, third quarter, and waning crescent. And there's kind of a cute way that we can kind of learn the phases of the moon. I want you to do a little Bob Ross time with me here. First thing I'd like you to do, leave yourself a lot of space at the top, and in the middle of your page, I want you to draw the Earth. Right in the center. And the Earth, we're going to choose the direction of the sunlight as coming from the right. So over here, we have to choose the direction of the sun. This is the direction that the sunlight is shining on Earth. And that means I can draw a line right down the middle of Earth. Let me improve that line. And this line is the boundary between the daytime and the nighttime of Earth. I don't suppose you guys know the name of that term, do you? This line is called the terminator. The terminator on any astronomical body is the line between the daytime and the nighttime shadow. So HR Astro. Here's a lovely picture of the moon to share with you. Look at that goodness. Can you guys see the terminator? That's the terminator right there. It's the boundary between the daytime and the nighttime side. Cool no vocab words for you. We're going to be studying this moon in detail, you know. You're going to learn so much about it. It's going to be amazing. Okay. The first thing to remember is that the Earth is a giant rotating clock. You just spent the first part of your lecture learning that. That means if I make a little arrow in this direction, what time is this little meridian arrow? What time is it at that arrow?
That'd be noon.
Yeah. What time is this arrow?
Midnight.
If you assume that we're rotating counterclockwise from north, what time is this arrow? What time is that arrow?
6 p.m.
Nice. This is 6 a.m. 3 p.m. 9 p.m. 3 a.m. 9 a.m. We cool? That's the rotating Earth. It's a big clock. I now want you to draw in some moons. Here's a moon. 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 8 moons. Here's a moon. Here's a moon. Here's a moon. I want you to draw the terminator for every single moon. This really kills markers. I used to love doing this on a chalkboard. I miss the days of chalk. Chalk's nicer on your fingers than dry erase marker too. I'm just complaining, some teacher complaints, that's all. While I fill in my happy little moons. This is what the phases of the moon look like from outer space. Sorry, that moon's a little off to the side. This moon is called the new moon. That's when you look at the dark side of the moon. This moon is the full moon. That's when you look at the bright side of the moon. This is the first quarter moon. That's when you see the moon as a half of a disk in your sky. This moon is the waxing crescent moon. The waxing crescent moon is when you look at a slice through the moon like this, but if you're seeing a pizza wedge of the moon, right? If you're seeing a little pizza wedge up there, you need to remember that the moon is a three-dimensional body. And that pizza wedge is actually more like a tangerine slice. And the moon is bulging its protuberant belly towards you, the viewer. However, when you look at the disk of the moon on the sky, the moon becomes rasterized or flattened. And because of this, the pizza wedge that you're seeing, it ends up looking like what they call in the Arabian Nights, the fingernail moon. You're seeing a tangerine slice, but because it's flattened onto a two-dimensional surface, the tangerine slice ends up looking like a fingernail. Now, the gibbous moon has a tangerine slice removed, so it has the shape of an egg rather than a full circle. So we have waxing crescent, we have waxing gibbous, that's the egg shape. Down here we have waning. By the way, waxing means to grow from new to full. Waning means to shrink from full to new. This is your waning gibbous. Why is it gibbous? Because you're seeing a cross section like so, with a tangerine slice removed from the moon. This is what's sometimes called third quarter. And this is waning crescent. You have now learned your phases of the moon. Class, what phase of the moon is this?
Is that waxing gibbous?
Yeah, it's definitely a gibbous moon because it's egg-shaped. This happens to be waxing gibbous. All right, let's look at this again. I can use this diagram as a tool to learn what time the new moon and the full moon will rise, cross the meridian, and set. So, hold on, does everyone have this? I need to erase it. Michaela, how you doing? Looks like you're writing.
Just give me 1 second. I'll be done with it.
My pleasure. Take your time. I'm going to do 2 micro sample problems with you, and then we'll take a little break. I'm sure you guys must be getting a little zapped out. Was that Ryan? Who said, or was that Dennis? That was Dennis. Dennis, let me know when you're all set.
All right, I'm all set.
Cool. Now look at your diagram, or look at the one that I'm about to put on the board, and here's what we're going to do. We're going to track the new moon. I want to know, when does it rise? When does it cross your meridian? And when does it set? Let me help you with that, since it's your first question. Look at the picture here. Let's imagine that you're an observer. If you're an observer and your meridian arrow points towards noon, that's when the new moon is on the meridian. And I'd like you to remember that your horizon is perpendicular to the meridian. So your horizon line goes through the center of the Earth, perpendicular. In this horizon, since it rotates counterclockwise, rising in the east, this is your eastern horizon. And down here, this is your western horizon. And this is rotating in a that way direction. Sorry, let me erase that. That sucked. The horizon's rotating in that way, so things will rise above the east, cross your meridian, and set in the west. What time does the new moon cross your meridian? This is supposed to be a softball. What time does the new moon cross your meridian?
Noon.
Very good. Let's try a slightly less softball. What time does the new moon rise? For it to be rising, we need it to be crossing your eastern horizon, right? Things rise in the east, last time I was told. Which way did, yeah?
Would that be midnight then?
No. This red line is your horizon line. Where is your meridian, if that's your horizon? I normally have a way to do this where I rotate in the classroom. I've never tried to teach this online before. Here.
Would it be
Look at
6
me.
a.m.?
Huh?
Would it be 6 a.m.?
Very, very good, because your meridian is perpendicular to your horizon.
Yeah.
So so remember, everything is rotating in this picture. Everything is rotating in this direction. So when the moon is rising up above your eastern horizon, your meridian is pointing to 6 a.m. That was pretty damn good. What time does the new moon set?
That'd be 6 p.m. then?
Excellent.
Cool.
Notice that the new moon is up all day, like a squirrel. How about the full moon? It has a rise time, a meridian crossing time, and a set time. Excuse me. Someone besides Brandon, so I know that I at least have two people. What time does the full moon cross your meridian?
Midnight.
Excellent.
12 a.m.
12 a.m. What time does the full moon rise?
6 p.m.
Awesome. What time does the full moon set?
6 a.m.
Damn, you're good. Who said that? Who is that? Michaela. Okay, Michaela. I got a harder question for you then. Since you're, oh, by the way, look over here. Notice that the full moon is up all night, like a raccoon. The new moon is a squirrel. The full moon is a raccoon. Ooh, I like that. It's kind of poetic. Hey, Michaela. I got a question for you. Where's your face? There it is. It's 3 a.m. and you're leaving the bar and you're drunk. You look out to the east and you see a crescent moon rising on your horizon. Is that a waxing crescent moon or a waning crescent moon?
If I'm looking at the east,
If it's 3 a.m. It's a crescent moon coming above your horizon.
so it would be waxing.
False. The waxing crescent moon is over here, and cannot be seen by an observer whose meridian points to 3 a.m.
Oh, okay, yeah. So then,
The waning crescent moon is coming up. So if you're leaving the bar, okay, the waxing crescent moon is the one that you see in the early evening around dinner time. The waning crescent moon is the one that you see if you've been up too late. Okay? You've just learned something important. Most importantly, what you've learned is with this helpful diagram, you can now figure out the rising and setting times of any phase of the moon. I know, for instance, that if I see a half moon or a crescent moon and it's around dinner time, that's got to be waxing. I know that if it's like early in the morning or very, very late at night and I see a crescent moon, that's a waning crescent. Okay, you've now learned a little bit about lunar phases. Here's my suggestion. What do you say we take a little pause and a tea break, because you've learned a crap load of stuff in the last hour or so. And then after a little sandwich break, we'll come, oh my gosh, let's give ourselves to like 10 past 2. Let's really indulge. Maybe 10 past 2 or so. Take a little break, and then we'll come back to it. Does that sound like a plan? I'd like to mention now, because you've got some time during your break, our lab today is not in the lab book. It used to be in the lab book before they changed it. So at some point, we should all print out under the lab section. We're going to be doing a somewhat confusing lab called eclipse prediction. And this PDF here, you'll want to print that out. We're going to, mostly the pages you need are this one, the eclipse data, and this one, the answer sheet. So 4.4 and 4.5. So I don't know. At some point, we got to do that. I have to print it too. So, okay. So I'm going to take a little break, and I'll see you guys at, let's say 15 past. Okay. Let's go nuts. Let's have a nice long break. Everyone like that? Yeah, me too. All right. I'm going to pause. I think we're ready to go. We're back from our break. Everyone's feeling a little rejuvenated. Got some sugar calories to the brain, whatever you need to learn more about the moon. Shall I start with a slide? Yes, I shall. Guys, let's talk about eclipses. The sun is like over here, where your little faces are. It kind of looks like every time there's a new moon, that the moon is in between the Earth and the sun. It kind of looks like every time there's a full moon, that the moon is on the opposite side of Earth from the sun. So why don't I have a solar eclipse every time there's a new moon? I get a new moon once a month, right? Shouldn't I also get a solar eclipse? Do we have a solar eclipse every month? Yes or no?
No.
No. But why not? Shouldn't the new moon block the sun?
No, because isn't the sun constantly moving too?
Okay, but on a single day, the sun's kind of located kind of that way, right? Any direction that is that way is sort of towards the sun. So the sun's way over there. So the sun's moving day after day by 1 degree. So in one day, the sun goes from there to like there. But on a single day, the sun's kind of like to the right. See, Brandon? The moon and the sun are in the same, well, I want to be careful here. I am trying to trick you after all. I have to be careful what I say if I plan on tricking you properly. Why don't I get a solar eclipse every time there's a new moon? In fact, let's try this. I am going to do a jazzy demo. I think it's going to be jazzy. Oops. Hold on. Okay. My leash is short. Why isn't this? Oh, because it's not plugged in. Hold on. I got it. Okay. Over here, I have the sun. Here's my sun. And here's the Earth and the moon. I wonder if I could make this better by turning on the lights. It's still kind of bright in here from sunlight. So now the front side of Earth is being illuminated. It needs to be darker. This would work pretty cool at night. Can you guys see the shadow of the moon on Earth here? Ooh. Okay. It turns out that this demo works a little better in the classroom. I usually have a very bright lamp with me. If the moon orbited in the same plane as the sun, if it orbited in the ecliptic plane, then every time the moon passed between the Earth and the sun, you would get some kind of eclipse. Do you see that shadow of the Earth there? There's my solar eclipse. Now, the reality is that the moon's orbit is not in the plane of the ecliptic, but it's inclined by about 5 degrees with respect to the plane of the ecliptic. So it's kind of going up and down and up and down. 5 degrees might not sound like much, but if the moon is 400,000 kilometers away, 5 degrees can put it significantly above or below the plane of the ecliptic. Okay, hold on. What I should be doing is relying on the book's diagrams. The book has a pretty nice diagram for this. They imagine the ecliptic plane is kind of like a sheet of water. And what you can see happening is, oh crap. Let me just get my draw tools here. They imagine the ecliptic as a sheet of water. And here you can see the moon coming up, plunging above the ecliptic plane, and then boof, plunging down into the ecliptic plane. And it's crossing the ecliptic plane here and here. Let's see if you guys can figure out what the phases of the moon are now that you're knowledgeable about the phases of the moon. Class, what is the phase of the moon there? Oh, snap. The red arrow points towards what phase of the moon? Just look at your diagram. Try to figure it out. Take a guess. You have a 1 in 8 probability, 16% chance of getting it right.
Would it be a warring crescent?
Wait. There's waxing and there's waning. It is not a crescent, however.
First quarter.
Who said that? Ian. You smarty pants, you. How did you know that?
I looked at my diagram.
Yeah. That's when the moon is at a 90-degree angle with respect to the sun, right? That's sort of like a 90-degree angle there, correct? Okay, Ian, since you're so good. Clear all drawings. I gotta change the batteries in my mouse. It's getting a little wacky-do. Well, what's that phase of the moon?
New moon.
How about this one?
Full.
Great. You'll notice, Ian, that in this configuration, the new moon is below the ecliptic plane. And it's still on a vertical line connecting Earth and the sun, but it's like below the ecliptic plane. So you're still going to see the dark side of the moon from Earth, but it's not going to be in the direct line of Earth and sun. On this configuration, as the moon's orbiting around Earth, though, Earth is sliding around the sun. And there are some times of the year when the moon will cross the ecliptic plane, and it'll cross the ecliptic plane just as it aligns with new moon or with full moon. And at those times of year, you will get an eclipse. By the way, I kind of want to go on a tangent for a second, and I want to show you guys a couple of pictures. Before I get into the eclipses and the shadows, I'd like to first I'd like to show you a picture of like a crescent moon. Let's look for a crescent moon together. Sorry, I didn't spell that right. And I want to show you block images. Have you ever seen this before? Ever seen the moon look like this, where you can kind of see the dark side of the moon? What's that all about? How come sometimes you can see the dark side of the moon and sometimes you can't?
Is that picture during the day? Or is that
You can see the moon during the day. Actually, it's probably, no, it's not during the day exactly, because you can see the star, you can see Venus here. And during the, well, actually, did you know that Venus is the only object that you can see during the day besides the sun and moon? Shakespeare refers to Venus as the daytime star. If you know where to look during the day, you can actually see Venus if it's far enough away from the sun. My guess is that this picture was taken around dusk. After all, the waxing crescent moon is usually up at dusk. But you're still missing my point. My point is, what the hell is this? How come I can see the dark side of the moon? How does that work? All right, let's ask a simpler question. Why can I see this side of the moon? How does the moon shine? Oh, snap.
From the sun.
Thank you. Guess what? I got a secret. You know moonlight? It's just fucking sunlight. Same thing. Okay? There is no moonlight. It's just sunlight bouncing off the moon. I guess that is moonlight, but whatever. You see the moon from reflected sunlight. So what the hell is this then, Brandon?
Is that from the reflecting off our Earth?
Very good.
There
This
we
is
go.
what the Germans call the Gegenschein, the against light. And did you know that not only does the moon go through a set of phases, but that Earth goes through a set of phases as well? No kidding, Earth goes through phases, and they're usually opposite the phases of the moon. So let's go to 78 again here. Click 78, please. What are you doing? Click 578. For instance, if you are standing here, I'm really loving the arrow tool today, and you're looking up at the waxing crescent moon, guess what phase people on the moon are going to see? If you're standing on the moon and looking back to Earth, what phase should it be?
Waning gibbous.
Very good. It's always opposite the phase of the moon. I want to show you guys a beautiful and iconic picture from US space history. The picture is so famous that it has its own name. It's known as Earthrise. And there's a cool backstory to this if you've never heard it before. During the Apollo moon missions, several photographers were tasked with photographing the far side of the moon. During one of these operations, one of the cameramen took an unscheduled and unscripted picture. He looked through the porthole of the lunar orbiter, and he saw Earth rising above the horizon of the moon. What phase is the moon in this picture, class? What phase is the moon in? In general, what shape is this?
That's the egg shape.
So that's what phase? Egg shape refers to what shape? What do we call that?
The waxing gibbous, right?
It's a gibbous phase. Maybe it's waxing, probably. I don't know. It could have been waning gibbous, but it's a gibbous moon. Think about it. This is the first time that humans had ever seen their own planet rising above an alien terrain. This picture was originally not considered important, and it was left in the drawing room at NASA. Carl Sagan dug it up and said, "Holy shit, NASA, we need to publish this photo. Do you realize how profound this is? It's the first time humans are seeing their Earth as a alien planet coming up over the surface of a foreign horizon." In fact, you can trace the beginning of the environmental science movement to the publication of this photo in the 1970s. It coincides with people doing research into climate change and other aspects. I think it's maybe the first time that people realized that their planet, it wasn't this garden of earthly delights where you can throw cheese wrappers on the ground and stuff. Suddenly, we started to realize that our planet was a fragile little ball floating in the harsh vacuum of space. And we're all kind of stuck to this thing, and holy cow, maybe we should take care of it because it's all we got, you know? In any case, it must be profoundly cool to see the Earth rising above the moon. What's the angular size of the moon on our sky? The radius of the moon is 1,700 kilometers. The radius of Earth is 6,400 kilometers. What is the angular size of the moon on our sky? You are supposed to know this. Does anyone know? Angular size of the moon. Go. Damn. You guys had been impressing me up until now. Now I don't think you know the angular size of the moon. I'm getting depressed.
Would that be using arc seconds and minutes?
How about degrees? I'll take it in arc minutes. Hell, I'll take it in micro arc seconds if you got it. I'll take it in any fucking angle. Just give me the number. Give me the number.
0.5 degrees.
Who said that? Where are you? Who knows this? Who got that?
I do.
Wait, is that Megan or wait, where are you?
No, it's Michaela.
Oh, Michaela, sorry. Michaela, yes. I can't see your face yet. I'm looking around. Okay, here you are. Yes, Michaela, you are the best. 0.5 degrees. Michaela, here's a thought question for you. It looks to me like the radius of Earth is 3 times bigger than the radius of Mars. I'm sorry, than the radius of the moon, kind of, right? 6,000 kilometers is 3 times bigger than 2,000 kilometers. What would be the angular size of the Earth as seen from the lunar horizon? How many degrees is this on the moon sky?
So if it's 3 times bigger, so it would be 1.5. So 1.5 degrees?
That would be very good. This would probably be like 1.5 degrees on the sky. Now think about that. The Earth must look huge from the sky of the moon. It must be this giant glowing orb. Now, have you ever been out camping at night on a full moon? Like, the full moon is so bright that it will cast a shadow on the ground if you're in a forest. Could you imagine if you were on the dark moon, how bright the full Earth would be? The full Earth must be like, it must be really bright because it's 3 times bigger than the moon. In fact, when you're seeing the Gegenschein, which I have since erased, the against light, you're seeing light that's bouncing off the Earth, and then the Earth light is bouncing off the dark side of the moon and then bouncing back to your eyes. You're seeing Earth light reflected off the dark side of the moon, which is pretty cool. The Germans call it the Gegenschein, the against light. Look for it sometime. It'll make you happy. So all of this gets me thinking about shadows and eclipses. Clear my drawings. Let's take a look at the geometry of shadows and let's learn our conditions for the moon. Let's take some notes. Okay. I'd like to start with the conditions for an eclipse. The 2 conditions.
I think you're lagging a little bit.
I've got some lag. You're lagging a little bit for me.
Yeah, like it says
Brandon,
network, or it says,
does my internet suck or does your internet suck? Michaela, am I lagging for you?
You're lagging.
yeah.
I'm summoning the internet demons. Better signal. Okay. I don't know what to do about it, guys. I'm sorry.
It says your network bandwidth is low.
Mine? Hell, it
Yeah, it
is.
says Brennan.
Let me close some tabs here. Maybe I got too
I
many
don't know.
tabs.
Oh yeah, I just got my lab printed. That's why I was
Cool.
gone for a minute.
Am I better
my
now
friend's
or am I still lagging?
You're still kind of lagging.
I'm going to proceed slowly in hopes that you can get some usable notes. I apologize. I don't know why. Normally my internet is good. The conditions for an eclipse. The phase of the moon must be new or full. That's condition 1. A new moon will give you a solar eclipse. A full moon will give you a lunar eclipse. Condition number 2. The moon must be at what's called a node. What is a node? A node is when the moon crosses the ecliptic plane. Sorry. A node is when the moon crosses the ecliptic plane. This happens twice a year. They're known as eclipse seasons. These eclipse seasons happen twice per year. That means 2 times a year you get some type of two lunar eclipses, and twice a year you get 2 solar eclipses. That's a total of 4 eclipses per year. But you don't always get to see them. You got to be in the right place at the right time. That means you got to be within the shadow of one of these objects. I know I'm glitching, but take those notes. I'm erasing now.
Oh, wait, hold on. Wait, hold on 1 second. It was super small and really blurry, so I couldn't see it all.
Sure.
What's the last eclipse seasons? There it is.
Eclipse seasons. Not only is my internet lagging, but our lectures are lagging behind schedule, so I'm getting a little freaked out, but whatever. We're just going to do this at the normal rate and see what happens. Brandon, can I keep going or do you need another second?
Yeah, you're good. I finished it.
Okay, I'm racing. Let's talk about the geometry of shadows. Not only are there 2 types of, or 2 conditions for an eclipse, there's also 2 types of shadow. There's a complete shadow known as the umbral shadow, and there's a partial shadow known as the penumbra, or the penumbral shadow. Two types of shadow. umbral shadow is a total shadow. A penumbral shadow is a partial shadow. I can even make some of these on the board sometimes. Let's see if I could do that. I've got a spotlight pointed here. Let's see if I can do this. In order for this to work, there has to be a correlation between the angles here. I definitely did this in a classroom once, but I've never tried it here at my house. Well, I think it's because my light is really small and my hand is big. I need the light source to be farther away. It works in the classroom when I have a larger projector. Let's just take a look at the diagram instead, since I'm obviously screwing that up. Class, here's a thought question for you. Pretend that you were a little bumblebee floating in space. How did the bumblebee get to space? I have no idea, but there it is. And let's imagine that your bumblebee, excuse me, is floating right here. There's your bumblebee. If you looked back towards the sun, what would you see? Can anyone answer that question for me? Will I change the batteries on my dying remote? What would it look like if you were a bumblebee where the blue squiggle is? If you looked back towards the sun, what would you see? All right, let's start simple. Could you see the sun? If you're here, can you see the sun?
No.
Yes or no? Megan, talk to me. It's up to you.
No.
You could. Megan,
Would it be no?
Megan, if you're here, if you're in the umbral shadow, the answer is no. You could not see the sun from the umbra. But you can see some of the sun from the penumbra. See, this picture shows you part of the story, but it doesn't show you why the penumbra is only a partial shadow. Could anyone answer what the sun would look like if you were located here? Here's a helpful hint. The sun is an isotropic emitter. Let me explain what I mean by that. If you take a little spot in the sun and analyze it, every single point on the sun sends rays of light in all directions. Every single spot on the sun is emitting photons in all possible directions. That spot is emitting photons. That means there are parts of the sun that are emitting photons here. What would the sun look like if you were standing at the blue dot?
Would it be almost like there'd be like a ring almost?
Not a ring. It would look like
crescent?
Yes. Who said that? Who are you? Zach, was that you?
I said crescent.
Oh, I don't know whoever that was. You're damn straight.
Yeah.
That's right. It would look like, I'm going to try to draw this. It's not going to be pretty. It would look like a fingernail that was pointed horns down. That's what it would look like. So you're still getting rays from the top of the sun, but the rays from the bottom of the sun are being blocked. I'm trying to explain to you why the penumbral is a partial shadow. I thought that would be interesting to you guys. Okay, so listen up. There's 6 types of eclipses. Let's write them down, and then I'll do show and tell picture time. Okay? Here are your 6 types of eclipse. There are going to be 3 solar eclipses and 3 lunar eclipses. We'll start with the lunar eclipses. The first lunar eclipse is called a penumbral lunar eclipse. A penumbral lunar eclipses happen when the sun is located, when the moon kind of is located where the bumblebee was. Annotate, we'll use white for the moon. I will use a filled circle. When the moon is located here, you get a penumbral lunar eclipse. That's when the moon is in partial shadow. When the moon is here, you get a total lunar eclipse. That's when it's in complete shadow. And when the moon is like this, when the moon is half in and half out, that's when you get a partial lunar eclipse. So there are penumbral lunar eclipses. There are partial lunar eclipses. And then there are total lunar eclipses. The solar eclipses are a little bit different. There's a partial solar eclipse. There is a total solar eclipse. And then there's a rare type known as an annular eclipse. We talked about that last class. That's where you get a ring. Take a second to write those down. Let's look at some pictures together. The first type of lunar eclipses happen all the time, but most people don't recognize they're happening. And that's called a penumbral lunar eclipse. During a penumbral lunar eclipse, the moon moves from outside any type of shadow, and it moves into the penumbral shadow, resulting in a slow darkening of the moon. The reason why most people don't notice penumbral lunar eclipses is because the penumbral lunar eclipse could take something like 6 hours. But most people just look at the moon for like a couple of seconds while they're running from their van to 7-Eleven. And if you just kind of look up quick at the moon and you see the moon there, you just think, there's the moon, screw it, I got to get to 7-Eleven. Only if you stood in the parking lot for 6 hours and stared at the moon and slowly noticed it going dimmer, would you realize that you were in a penumbral lunar eclipse. And at that point, you might be considered insane, all right? So usually people don't even realize these are happening. During a partial lunar eclipse, that's when you notice something is happening, because you suddenly start seeing a bite getting taken out of the moon. Partial lunar eclipses are of interest historically. It is said that Aristotle argued that Earth must be a sphere based on the facts that Earth's shadow on the moon was curved. Very clever of you, Aristotle. Wish I had thought of that. Lastly, you get something called a total lunar eclipse when the moon passes into the complete umbra. You would think this would result in a completely dark moon, but there's a cool optical effect that happens during a total lunar eclipse. You know, if the Earth had been an airless rock like the moon, then when the moon was in the Earth's shadow, you would completely block the sunlight and the moon would have been dark. But the truth is that the Earth is surrounded by a fluid of atmosphere, the air that we breathe. And air can bend sunlight kind of like a lens or a prism does. Here. In the same way that glass can bend light, creating some cool optical effects, the atmosphere of Earth also bends sunlight. And it bends sunlight around the curvature of Earth, but as it does so, it filters out the blue light, that gives us the blue sky, and only the red light from the sun can curve around the lens of Earth's atmosphere. That red light then strikes the moon and bounces back against Earth, resulting in totality, a point where the moon suddenly turns an evil blood red color that terrified ancient peoples. Let's see if we can find a groovy internet picture of a total lunar eclipse in time lapse. Some people have very nice astro photos of this. And there's one in particular that I remember was really, really cool. Yeah, here you go. Now, I don't know if you guys remember, but a couple of years ago, in the middle of January, we had a total lunar eclipse. And I remember because I was at a party and I stepped outside. It was like 5 degrees out. It was brutally cold. So cold that you don't even want to be outside for 50 seconds. And I looked up at the moon in totality, and it was this evil red color, just like this. The only difference between the real vision and this picture is they've adjusted the exposure on their cameras here. The moon looked significantly dimmer during the total lunar eclipse. This photographer must have taken a longer exposure image so that the red moon looks as bright as this moon, but that's not how it was. You saw the moon get darker and darker and during totality. Did any of you see that, by the way? Because that was only a couple of years ago. How many of you saw that? It was around midnight, so you had to be. You saw that, Zach?
I'm pretty sure.
It looked pretty fucking evil. You'd be hard pressed to forget it if you ask me. Anyone else besides Zach and me see that thing? It was like it wasn't this past January. It was the January before that. Well, look. The cool thing is we can see these eclipses frequently. Lunar eclipses are, every time there's a lunar eclipse, you have a 50-50 chance of seeing it. If you're on the daytime side of Earth, you're not seeing it. If you're on the nighttime side of Earth, you can see it. And NASA runs a pretty rad total lunar or lunar eclipse page. And you can get the dates and times of all the upcoming ones. Let's see when the next time we'll be able to view a lunar eclipse. That might be a cool thing to keep track of. It takes a few seconds to understand this. They're doing them also in universal time, usually. Let's see. We are in oh, wow. We're already in 2020 here. What month is it? Oh, you'll notice that in 2020, there are, holy shit, 4 penumbra lunar eclipses. So you'll be able to see the one on July 5th is kind of coming up, isn't it? Is our class still running on July 5th? That's next Friday. There's going to be a penumbra lunar eclipse next Friday. Oh, sorry. June, yeah. Was that?
Oh, yeah. So June 5th.
No, but that one's only visible from Europe and Africa. Sorry, July 5th. Anyways, penumbra lunar eclipses suck. I'm not going to lie to you. Let's look at the next window. Hold on, I'm feeling dumb. Oh, here. Why does it go from 2020? Oh, 2021. How about next year? Anything good? There's a total from the Americas. There we go. May 16th, 2022. Mark your calendars. You'll be able to see 2 years from now a total lunar eclipse. Let's check it out. It looks like universal time, the greatest point of totality, occurs at 400 hours Greenwich, England time, universal time. What time will that be for us in Rhode Island? If it's 400 hours England, if we're off, what time will that be for us? How many hours are we from Greenwich again? I'm trying to teach you how to use your class skills to answer cool questions like when your kid brother wants to know about the next lunar eclipse. Eastern Standard Time is how many hours from England? Amber. Oh, 5. She's saying 5. Yes. I'm sorry. A little slow on the uptake today. So Amber, what time will that be? 4 hours minus 5 is what time?
I don't know. Is my mic 1?
No.
No.
Anyone? If it's 4 a.m. in England, what time is it in Rhode Island?
Be 9.
Oh my God. Is there a razor around here?
11
Because I just
p.m.
want to slit my wrists and go jump into the
11
bathroom.
p.m.
Thank you.
11
11
o'clock.
p.m. Okay. You'll be able to see that eclipse at 11 p.m. Thank you. Okay. Let's get back to the action here. Am I in share mode? Oh, can you guys even see my screen? What the hell am I? Yo, I am
No.
in share mode. Okay. Anyways, you can see me now. Oh, let's look at solar eclipses real quick. Oh, we're running out of time. Ugh. I've got another module that I must do with you guys. Solar eclipses are more rare to see because the shadow of the moon on Earth is smaller. So in order to see it, you've got to be right here. If you are located here, you will see a total solar eclipse. If you are located there, you will see a partial solar eclipse. And if you're located here, you will see no eclipse. Did y'all know that there's 2 types of month? Let's take this as some notes here. I got two more things to do with you before we start lab. We have one more homework problem to do that we didn't finish. There are 2 types of month. Months are obviously related to the cycles of the moon. It's possible to keep calendars by the moon as well as by the sun. There is a sidereal month. A sidereal month is the true 360-degree orbit of the moon. A sidereal month takes 27.3 days. That's the true orbit of the moon. There is also a synodic month. In Latin, a synod is a meeting point. So here's some new Scrabble words for you guys. Synod means meeting. A synodic month is the time to go from new moon back to new moon. And that is closer to the calendar month. It's 29.5 days. You might be wondering why. I have an excellent diagram which will explain it to you. First, I have to find it. Examine, if you will, slide 6. Class, let me get my arrow tool. Let me change the color to cool purple. What phase of the moon is that? Oh, I gotta, hunched over this computer is going to give me a bad back. I should use the stool.
Is that new moon?
How'd you know that? What made you so smart? Where'd you get that answer from?
Because the moon is aligned.
I'm
The moon
sorry.
is aligned with the sun.
Yeah. Very good. By the way, who said that? Because I was busy stretching my back.
Brandon.
Brandon, thank you. Okay, Brandon, since you're so cool, look at this moon over here. Would you agree with me that that moon has done a complete 360 revolution around the Earth?
Yes.
Good. What phase is the moon in that second picture?
Waning crescent.
Excellent. You know your stuff. Notice that the moon needs to rotate an extra, I can't remember what it is, I think 15 degrees an extra 3 days or so to get back to new. Hey, Brandon, suppose you were a pig farmer in ancient Rome, and you didn't know much about much except pigs and shit and looking up at the sky because you're a pig farmer. Do you think it'd be easier to keep track of the sidereal month or the synodic month?
Synodic.
Yeah, why? Why would a pig farmer in ancient Rome know about the synodic month but not the sidereal month?
Because you can go off of new moon, full moon.
Yeah, you can see the new moon and you can count the days until the next new moon, right?
Yep.
If you were a pig farmer in ancient Rome and you wanted to become an enlightened pig farmer, someone who didn't merely shovel shit for Milord, but instead was a court astrologer, eating Cornish game hen and divining the future of kings and queens, how would you deduce a sidereal month? You'd probably be screwed. You'd probably get your head cut off. Anyways, okay, look, that's a harder question to answer, and I'm going to explain it to you. But let me do that. In addition to there being 2 types of month, there are also 2 types of planetary period. Now, to get into this, I'm going to have to teach you some old-timey astronomy, the kind of astronomy that court astrologers would need to know about. These are some terms from ancient astronomy lore. Opposition, okay, so let's walk you through what's happening here. This symbol is the Earth. Do you see that symbol, a circle with a cross in it? That's the astrological symbol for Earth. This is the symbol for Venus. Venus is an interior planet. And out here we have an exterior planet like Mars. Okay, notice that when Mars is opposite the sun, it bears the same relationship that the moon does during what phase? I want to use red for Mars, by the way. This planet is Mars. It is currently opposite from Earth, or opposite the sun from Earth. When Mars is in opposition, it bears the same geometrical relationship as what phase of the moon?
Would that be waxing crescent?
False. What did someone else say?
Noon.
That's also wrong. What phase is it when the moon is opposite the sun?
Full moon.
Yes. Who did that? All your faces are, my internet connection is fucked up, I think. Who got the full moon right? I want to talk to you. Was that you, Michaela? Okay. Sorry, this is helpful for me to learn you guys, learn your names and stuff as well. Michaela, when Mars is in opposition, could you tell me what time it crosses my meridian?
Hold on. Let me look.
Yeah, do it. You could do this.
12 a.m. Midnight.
Very good. What time would Mars rise at opposition?
It would be the same thing.
So keep going. Tell me.
So if it was rising, it would be at 12.
Nope. No. It's 6 hours off, right?
So it'd be 6 a.m.
Right, because if this is your meridian, this blue line is your horizon, like so. So you'd have to rotate back 90 degrees so that the meridian pointed sort of up, right? That probably didn't make any sense. Look, Mars in opposition rises at 6 p.m., crosses your meridian at midnight, and it sets at 6 a.m. There's some chatter here. Where's that coming from? Can you guys hear that? Yanita, that was you. Yanita, it sounds like the Death Star was trying to communicate with you, or whatever that was, robots from the planet Zargon. Don't forget to mute yourself from time to time so that I don't hear that. Okay. Well, I heard some crazy stuff, and then I clicked mute because I can mute you, and when I muted you, it went away. But all right, in any case, I don't hear it now, so let's not worry about it. If I was a pig farmer in ancient Rome, I would know when Mars was in opposition. And here's why. Mars would rise exactly at dusk at 6 p.m. It would cross my meridian at midnight, and Earth would be closer to Mars, so it would be brighter than hell. But I'd only be able to keep track of one type of period, and that's called the synodic period. Let's take a look at this diagram. This is the last module I'm going to do before lab, so try to just keep your stamina up. Earth, Mars, and the Sun are in alignment. Mars is in opposition. Earth has a period of about 1 year. Mars has a period of about 2 years. During the course of 1 year, Earth goes all the way around the Sun. During the course of 1 year, Mars goes roughly halfway around the Sun. Then, Earth moves forward in its orbit, and 1.5 years later, it starts to catch up with Mars before Mars has completed an orbit. Now, unfortunately, if you're a pig farmer in ancient Rome, all you know is that Mars is back in opposition and it's crossing your meridian at midnight. That's called the synodic period. The true sidereal period of Mars is different than that. Let's start the recording. Okay, well, I hope you all remembered that because I forgot to start the recording again. Who said that? Thank you so much. Amber, thanks for catching me. We just missed part 2 of our lecture because dummy me forgot to record. But at least we'll have the lab recorded, right, Amber? That's something. I'm so sorry. Another good thing, Amber, is that we'll get the final homework problem recorded. If you are tuning in outside of normal class time, I don't think anyone actually is, but if you are, you missed phases of the moon, eclipses, and that's it. Okay. I'm deeply sad that I lost that. I would have loved to have that recording. Okay, let's try a sample problem. We're now going to do our final homework problem. Do you have this? Is it all, Megan, do you have that?
Yes.
Everyone else, I'm going to erase.
What number is this?
Great question.
We just did 53, I think.
We need, the last one we have to do is 51.
Can you read that for me? What's the title?
Hold on. It's orbital and, I'm sorry, I can't. I lost the page, hold on.
Look, I printed it out for you. It's right here, right? Orbital and synodic periods. Yeah?
Yeah, that was it. I accidentally closed my window.
Okay. I understand. I have a million glitches a day like the one I just had.
Use each object given synodic period to find its actual orbit period.
What's the synodic period of the first object?
It's Saturn and it's 378.1 days.
Okay, we can't leave it in days. We have to convert it to years. I'm putting you all on the express line here. What's the conversion from days to years? I refuse to move forward until you answer that question.
Is it 365 over 1?
Where does the 365 go again?
On top. Oh no.
Haha. You messed up, didn't you?
Yes.
But you caught yourself. Am I talking to Tess right now?
Yes.
Tess, very good. You caught yourself. 1 year is actually 365. Hey, how many sig figs, Tess?
3.
False.
Oh, there are 4 there.
If we use 365, we won't have enough sig figs. A sidereal year is 365.25 days. That way we don't have our precision ruined by the number of days in a year.
Okay.
Do the math, kids. How many sig figs are you going to keep?
4.
All right, what's the answer? We need to move quickly, please. I'm sorry, it's kind of my fault, but we need to move quickly anyways.
It would be 1.035.
Very good. Units?
Year.
Excellent. We now need to plug this into one of the planetary period formulas. Is Saturn an inner and an outer planet?
Inner.
Huh?
Is it inner?
Hey, my very educated mother just served us nothing. Where's Saturn?
Outer.
Thank you. So we're going to use this formula. The sidereal period is the synodic period divided by the synodic period minus 1 year. Please use parentheses. Set it up as follows. 1.035 years divided by open parentheses 1.035 years minus 1 year, close parentheses. You will punch it exactly as I punch it with your parentheses. Watch my moves and punch after me. 1.035 divided by open parenthesis key 1.035 minus 1 close parenthesis key and then equals. What did you get?
I got 29.571.
How many sig figs can you keep, Brandon?
4.
So give me the final answer with units.
29.57.
Units.
Days.
False.
Years.
Correct. Box it. Let's do part B, and that'll be good enough. Brandon, what's part B?
Mercury's synodic period is 115.9 days.
Let's convert it right to years. Days to years. 1 to 365.25. Do the math. Hey, Dennis, what do you think? Dennis, punch up for me. Tess? Oh. Anyone? Somebody please tell me the answer. Remember the old days when the nuns used to be able to beat the students with rulers? I bet that was fun.
What's that number on the bottom?
365.25, the sidereal period of Earth.
Is it 0.317?
Yeah. 0. Can you do that one more time for me?
317?
I need 4 sig figs.
3 is that last one.
What are the units? Was that Michaela? Who was that?
Amber?
Or Amber?
It's years?
Correct. Okay, Mercury is an inner planet. We're going to use the other variation. Synodic period, or the sidereal period, is the synodic period divided by the synodic period plus 1 year. Or 0.3173 years over 0.3173 years plus 1 year. What's that equal? Sorry, I was thinking maybe you could see my calculator if I did that, but divided by open parentheses plus 1 close parentheses equals.
Would it be 0.2408 years?
Round proper. Round proper.
0.241 years? Or
No,
do you
that's
want
3 sig. I want 4 sig figs. This is not a sig fig. These are.
Okay. 09, because it's 7, so you round up.
That's what I wanted to hear. Okay, we're going to skip part C because we really are behind schedule today. I don't want to keep us past 4. That's a promise I made. Everyone get that down. I'm going to print out today's lab if I haven't done so already. Hit print. 1 copy. Let's take a walk over to our lab room, shall we? You know, this has been the first time that I ever forgot to hit record after tea break. And I'm really, really sad about that. Thank God that Amber caught us when she did. Right, Amber? On the other hand, it's so sad because I lost the recording of all that cool stuff about eclipses. And I really enjoyed that part of the lecture, personally. I don't ever want to do that again because I want to have a record of all this stuff. So I may have to start recording through tea break because I'm obviously 50% of the time too forgetful to remember to hit record. That's lame that we're going to have all that downtime, but I don't, maybe I've got to get a sticky note and put the sticky note on the computer that says press record. And I'll put it like right there so I can't miss it. But I'm even going to forget to put the sticky note there. So can you guys help me with that? That's really important. Okay. Let's talk about our lab today. We're going to play Where's Waldo with eclipses. We are hunting for lunar and solar eclipses. And we're going to be doing the express version because we're a wee bit behind schedule. Do we all have our eclipse prediction handout? Let's go to, just a moment, guys. You got this? If you want to have some good feng shui, I'd like you guys, let me see if my Wi-Fi is still on here. I want to set up your feng shui. Watch how I set mine up. I'm going to go to my phone view here. Share screen, iPhone, share, pray to the internet gods, please. Please come up. I don't have time for any, yes. Okay. Come on, Zoom. Oh, yeah. All right. Let's go sideways. Whoop, whoop. Can you guys see that? See what's going on there? I've got the data on the left and the answer key on the right. Let's get a little more sunlight here. We're only going to turn this page.
So is this sheet basically the lab?
Yeah, this one sheet. You're going to need this for the data, but this is the sheet name. AS1010. Okay, class, from our lecture today, what are the two conditions for an eclipse? Do you remember that from our lecture today?
It'd be in new or full phase. It has to be in new or full.
That's one.
And then the moon must be at a node.
Node, that's where it crosses the ecliptic plane. Okay, this lab really works well in person because I usually do a demo with globes. I'm going to skip that. Let's go over here. We're going to be looking for 4 eclipses. 2 eclipses are going to be solar eclipses. 2 eclipses are going to be lunar eclipses. Let's put lunar and solar in the box there so we remember which type of moon gives us a solar eclipse, which type of moon gives us a lunar eclipse. Can you guys follow along with me there? All right. Let me go like this. Notice that for the year 1999, they've given us the exact date and time of the new moon. They've given us the exact date and time of the full moon. And then there are 2 nodes, an ascending node and a descending node. The idea is that, let's use my thing here. Actually, I could use some scrap paper, which I have. Okay, check me out down here for a second. If this represents the ecliptic plane, so if this is the sun and this is the earth, remember that the moon sometimes swings up in an ascending node and sometimes it swings down in an descending node. You're never going to have the time of the node perfectly match up with the vertical alignment of Earth and the moon. So for instance, notice that in this month, the moon occurred at Jan 17 at 1500 hours or 1600 hours, but the ascending node was January 15th at 200 hours. Now that node is nowhere near the moon, so they're not going to happen. But if they're only a few seconds off or a few minutes off, you probably will have an eclipse. Here's our first rule that we go by. The rule is 28 hours. If the time of the moon is less than 28 hours of the node, then pow, you get an eclipse. So we're going to play, have you guys ever played 21 blackjack before? We have to count the cards, and if you go over 21, you're busted. This is just like 21 blackjack, except it's 28 blackjack. We're going to have to count the number of hours and days from the moon to both nodes to see if any one of those nodes could have been 28 hours apart. Now, how many hours are in one full day?
24.
So, Zach, you would think that if they're more than a day apart, no eclipse can occur. But that would be wrong. And let me show you why. Here's a diagram of 3 days. Let's say a Tuesday, a Wednesday, and a Thursday. And Zach, you know that there's 24 hours each day, correct?
Yep.
So Zach, imagine if I had a new moon or something, at like 2,300 hours on a Tuesday. And suppose I had a node occur at 100 hours on a Thursday. How many hours apart is the moon from the node in that case?
That'd be 26 hours.
And that's less than 28 hours, isn't it? So although it's unlikely, it is possible to have a moon on a Tuesday and a node on Thursday, 2 days apart, right?
Yes.
So we're going to actually have to count anytime the time of the date of the moon and the date of the node are 2 days apart. Then we count hours. So here's how we're going to make this simple for ourselves. Let's start January 17th. Do you see how it says 1546? Let's cheat to keep our brains sane, and let's just round it up to 1,600 hours. Can you guys do that for me? Is January 17th 2 days apart or less for January 5th? Yes. Oops. January 17th, January 5th. Whoa, my whole thing is upside down now. January 17th, are those 2 days apart?
No.
No eclipse. January 17th, January 19th, are those 2 days apart?
Yes.
We need to count hours. Which came first, Jan 17 or Jan 19?
Jan 17.
How many hours were left in that day if it's 16 o'clock?
8.
Yep, so have your calculator handy. This could be useful. 8 hours plus, okay, what happens between Jan 17 and Jan 19? I think we call that Jan 18, right?
13.
How many hours are in Jan 18?
24.
8 plus 24 equals what?
32.
You're busted. No eclipse in January. Let's move on to the next date, Feb 16th. They say 639. We're going to round it to 700 hours. Holy shit, we got 2 ascending nodes on the same month. That's because the synodic period of the moon is only 29.5 days, but February, well, sometimes it's 29 days. Man, that's confusing as hell. Okay, whatever. Feb 16, Feb 1, Feb 28, doesn't look like we got any goose there. Feb 16, Feb 15, we got to count. Feb 15 comes first, 2,200 hours. How many hours are left in that day?
2.
2 plus, how many hours into Feb 16 are we?
7.
What's that give us?
9.
So?
We got one. We got
one. And we're going to use the time of the moon, not the node. I'm going to write down Feb 16, 639 on this sheet here. So these, this is the solar eclipse. So write Feb 16. Next up, we have to convert to local date and time. How many hours? This is universal time, by the way. How many hours is Rhode Island off from universal time?
5 hours.
So what should I write for the local time?
Would it be 139?
Very good. Okay, central or partial? Just a second. I have to sharpen my pencil. This is kind of a difficult lab to get started on, so let's see here. Central or partial? The rule for central is like a total or an annular eclipse. Central is the same as umbral in lunar eclipses. That's if you're between 0 and 20 hours apart. If it is partial or penumbral, that's when the eclipse is 20 to 28 hours apart. That's the rule. Now, we had 2 hours here, 7 hours there, 9 hours apart. So which are we?
Central.
Very good. Just follow along. North or south of the ecliptic plane is kind of tricky. You kind of have to do this. Let's make a dashed line representing the ecliptic plane. Okay? Did this eclipse happen during an ascending node or a descending node?
Descending.
That means the trajectory of the moon during this eclipse was like headed downwards, right? And the node happens here when the moon crosses the ecliptic plane. Did the node come before or after the moon?
Before?
Node came before, moon came after, right?
Yeah.
So here we are. It's headed down, node first, moon second. Which are we, north or south?
South.
Very good. Total or annular? This has to do with apogee. If the time of the moon is less than 8 days from apogee, you will have an annular eclipse. Apogee occurred on Feb 9th. The moon occurred on Feb 16th. How many days apart is that? 7. That means less than 8 days. It's annular, right?
Annual.
Cool. Possibly visible from our location. What time did this happen at Eastern Standard Time?
139.
Is that morning or afternoon?
Oh, that's morning.
Yep. Can you see the sun at 1:39 a.m.?
No.
And you can't see no fucking solar eclipse. All right. Let's keep moving. Can you guys help me find the next one? What do you say I speed things up a bit? Normally,
Can
I like
you
to make it,
can you quickly go to number 2 on the solar eclipse on the worksheet, just so I can see the time? What's that say? 139. All right, good.
yes, sir.
All right, almost set. Thank you.
I'm trying to strike a balance between teaching you and getting through it. You know, those aren't always the same thing. I spy with my little eye another solar eclipse. Can you? Where's the other solar eclipse? You're looking for a date of moon and node. Don't look at the full moon. Compare the solar to the ascending and to the descending columns.
Oh, August 11th.
Booyah, you rule. Brandon. They happen on the same day, don't they?
Yep.
Roughly, oh, get out of here. Sorry. How many hours? That's like 2 o'clock and that's like 11 o'clock, right?
Yep.
So that's what, 9 hours apart? I think.
Yes.
August 11th at 11:08. That's our time. How many hours off are we from Greenwich, England?
Five hours.
Except Eastern Daylight Time. Shit, here we go. Eastern Standard Time is UT hours minus 5 hours. Eastern Daylight Time is UT minus 4 hours. Remember daylight savings? God damn it. We observe daylight savings time from April to October. That means standard time is like during the winter. Daylight savings time is during the summer.
So it would be 7:08.
That's right. It's minus 4 hours because it's EDT, not EST. Sorry about that. And that's EDT, Eastern Daylight Time. Okay, central or partial is about whether they are more or less than 20 hours. This eclipse was only 9 hours apart, so I'll speed things up and say that it's central. North or south of the ecliptic plane. Was this happening during an ascending node or a descending node?
Ascending.
So this time the moon was going like this, up through the ecliptic plane. The node happened there. Did the node come before or after the moon?
Before.
Node came before. So that means node first, moon second. What do we got?
North.
Yeah. To get the total or annular, we have to see if it's less than 8 days from apogee. The time of the moon was Aug 11th. The time of apogee was Aug 20. How many days apart is Aug 20 from Aug 11th?
9.
That means it's total, not annular. This eclipse occurred, solar eclipse occurred at 7 a.m. EDT. Can you see the sun at 7 a.m.?
Yes.
Probably, especially in the summer. Let's look for the lunar eclipses. One of the lunar eclipses is kind of tough to find, so I'm going to find it for you. Jumping Jesus. I can see 2 full moons in the month of January. Do you guys know anything about that?
Isn't that blue moon?
Yeah. If you have a second full moon in the same month, the second full moon is known as a blue moon. How many blue moons were there in the year 1999?
1, because once, 2.
Yeah, 2. What's the day directly before and after January 31st?
January 30th.
Simple enough question, right? What's that, Zach?
January 30th and February 1st.
It looks to me like we got ourselves a node on February 1st. Let's count the hours. If that's 16 o'clock, how many hours were left in that day?
8.
8 plus 13 hours into February 1st. What's that give us?
21.
21. That means we have an eclipse in January. Jan 31, 1606. Is that Eastern Standard Time or Eastern Daylight Time?
Standard.
So 5 hours, Jan 31st, 1106. Umbral or penumbral follows the same rules. Umbral is within 0 to 20 hours of the node. Penumbral is 20 to 28 hours. How many hours apart were we again?
Penumbral.
21, so it's penumbral. Very good. This lunar eclipse took place at 11 a.m. Can you see the moon at 11 a.m., the full moon? What did we learn about the full moon during our lecture today? The full moon is like a blank. No one remembered my witticism, huh? I'm used to it. The full moon is like a raccoon. When are raccoons up?
Night.
That's right. The full moon's up all night. So, can I see a total lunar eclipse at 11:06 EST?
No.
No, because it's daytime. Can you guys find me the other lunar eclipse? Take 2 minutes. Look at the sheet. See if you can find it. I'm going to do something funny. Can you guys find me the last lunar eclipse? If you find it, just shout it out. Meanwhile, I'm looking for something.
Is that August 26th?
Let's deal with August 26th for a second. August 26th and August 25th, which came first?
August 25th.
If this is 10 o'clock, how many hours are left in that day?
14.
14 plus 23 gives you what?
No, that's wrong.
You're busted. Keep looking, Brandon. You had the right idea. You had the right spirit. Keep looking. Meanwhile, I'm looking for something different. I'm looking for a different type of eclipse. Sorry, I'm looking for something.
Would it be July 28th? There's 2 descending nodes, though.
That's okay, as long as it matches one of them. July 28th is correct.
Would be...
Hold on, I'm looking for something. So what are you going to write down?
Would be 11 plus... No, because it would be...
It's January 28th, 1125.
July 28th.
Oh, sorry. I was just testing you, obviously.
July 20. What's the time?
1125, right? Hold on, I'm looking for something.
That would be minus 4 hours. 10. Then it would be 7:25 for the next one, for local date and time.
Yeah. Damn it, I lost a video that I really wanted. You're right, guys. I'm sorry. I'm doing bad. I was looking for something cute, and it's totally not worth what I was doing. All right, July 28th. I'm sorry, you subtracted how many hours?
That would be minus 4.
So 7:25, correct?
Yep.
Okay. How many hours apart were these two moons? Was it more than 20 or less than 20 hours? This one was at 2:38, or let's say 3 o'clock. And this one was at 11 o'clock the previous day. So there's 12 hours, 13, 14, maybe 15, right? That means this is an umbral eclipse. Can you see the moon at 7 a.m., the full moon?
No.
Congratulations. You discovered all 4 eclipses, and you can be an astronomer to the king of the court. Yay. Okay, so where's my Zoom here? Guys, I pushed pretty hard on that one. I kind of rammed it down your throats, but we got done before 4, didn't we? Despite all of our foibles. So somehow we achieved our objectives. We did our homework. Sorry? We achieved our objectives. We did our homework perfectly. We had a nice long lecture where we learned way too much stuff to remember. And we did a lab, and we finished by 4 o'clock. So the only bad thing we did is forgot to record half our lecture, and I'm feeling pretty sad about that. I'm going to take one more second to see if I can find this NASA footage of a blue moon. I had it on my computer in the lab room, and I tried to like hastily grab all of my files. And it's just not there. I don't think I didn't grab it all. Let me just see if, yeah, I'll never find it again. Okay, it's all right. I'll show it to you guys in another life. Any questions, thoughts, or comments?
So we have class Friday.
Right. Thank you.
Friday at 10.
Yeah, I'm so glad. I forgot to. So everyone got the email that I sent about no class on Monday, right? Yeah. Now look, I'm not any happier about having class on Friday than you guys are. Normally on Friday, I'm riding my bike by the sea, I'm playing my synthesizer, and I'm drinking Bloody Marys in the sun. That's where I would like to be as well. But we got a job to do, and we're going to get together and we're going to do it and follow the CCRI schedule, correct? Okay. Thankfully, this will be the only time that happens. Honestly, it wasn't much of a day off because we have to make it up on Friday, but you have to understand that during a summer class, we have so few hours together. I normally have 15 sessions with a fall or a spring semester, and I only have, I think, 13 or 12 with you. It's ridiculous. And I want to give you the same education and teach you about cool stuff like planets. So we can't afford to miss a day. We're going to have to meet on Friday. It'll be the same schedule, Zach, as it always is. Around 10 o'clock, I send the link. We do as much of the homework as we can. We have a lecture. We do a hasty lab, and we bounce. Okay?
So unfortunately, I won't be able to make it on Friday because I have work. But I can like get all the work done by watching when you record. So I can get it like maybe Saturday morning.
Michaela, that is exactly why I'm going to hit record. Let's hope I don't have a boo-boo like today, right? Or you'd miss half the lecture. You guys, the rest of you will show up and keep me company, right? I don't want to be talking to an empty box here.
Yeah. So I have a question.
Yeah.
So Saturday is my birthday, and then Sunday I'm going with my friend to visit another friend in Florida.
Holy
for a
shit.
week. So in Florida, I'm gonna like be here and stuff.
Oh, but you'll be in Florida?
Yeah. So we're leaving on Sunday morning at like 5 in the morning or 6 in the morning.
Oh my gosh.
So we should get there around Sunday night, maybe a little early in the morning.
You're worried you might be
Monday.
a little, you're worried you might be a little too burnt to actually make it for 10 a.m., huh?
Well, I don't know if I'll be a little burnt. I just might be a little bit like, I might show up like at 12 for the meeting.
That's fine.
And
Zach,
then I'll just do the homework after. And look at it.
same deal for Michaela. The reason I record these is so that if we have personal stuff going on in our lives, you'll be able to catch up later. But you're not going to have a ton of time to do it. If I was in Florida, I'd want to drink pina coladas and look at the pink flamingos, you know? So that will be a distraction. But just, if you have to skip, just do whatever you got to do. Just get the work done, okay?
Okay.
And that's fine. As long as a couple of you show up to hang out with me, I won't be sad. So that goes for everyone. If something shows up, I'm recording these things for a reason. In some ways, it's kind of better than a normal semester, because if this was in person, I wouldn't be recording it. It would be harder to do that. But now you kind of have a get out of jail free card, which is great. So yeah, Zach, watch it when you can, do it when you can, just get something to me.
All right, thank you.
Ian, if you're still around, did you figure out how to submit that work proper? You're muted, buddy, sorry.
I was going to ask you after class whether or not if you got what I resubmitted. And if that didn't work, I was going to try again. It was, I believe I did the homework first.
This is my needs grading section. Let's see if you're in here. And you can all see this, so you can see what I have to go through when I grade. Here we go. I now have homework 1. Here, let's do it by item name. Ian, I see you for homework 1.
Yep. That's the only thing that I uploaded. So after this, I'll upload the rest. I just want to make sure that it worked.
It did work. Oh, let's click on you, and I'll have to look at Megan's attempt again. You'll be able to, you've got the work done because you were there with us, right?
Mm-hmm.
So that's Megan's. Oops. Here's Ian's. Yeah, bud, looks pretty good. I'll give you points for that. Is everyone else gonna make sure they turn that stuff in?
I just submitted the homework in the lab from today. Can you make sure that you can see it?
Yeah, I would like to do that. Let's go back. Let's go back. Was that Megan talking? Was that Meg?
Yeah.
Hold on. Here's eclipse prediction. Oh, you guys are right on top of it. I love it. Look at you guys. Megan, I see your eclipse prediction. Megan, I see your homework too.
Okay.
Look how fast these other students got that up. I'm very proud of you guys. That's the idea, right? We just get it all done, and then you don't have to take it to Florida with you, right? Or something like that. And Michaela, don't worry about the work on Friday. You can watch the video later. It'll kind of suck watching it at night after work, but actually you'll have all weekend, right? So you want to do it on Sunday? That's fine. Just don't forget, okay? As usual, had a great time hanging out with you guys. Any other questions or things we ought to think about before we end today? We're meeting on Friday if you can. Yeah. So cool. I'll see you guys on Friday, okay?
Sure.
Bye.
Thank you.